8-9 ওই তোমার নাম্বারিংয়ে চলে গেছি প্লে করে দাও এক্স্যাক্ট টাইমিং Five people wearing red today. Dada is wearing, he is wearing, these two wearing, I am wearing. Oh, that is also red. 6. Where are the students? They are on the way? They are walking or?
Yeah, they are. The hostel is 2 kilometers away from
Oh.
hostel you are staying. But there is a road in through this. Right? When will we start?
Yes, ma'am. It is not coming? Hello, 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 hello. So, they are walking, do you know how long it will take? If it 2 more minutes I can wait, if it is like 10-15 minutes.
No, we will just start. Interest of time, start.
We will start?
Okay, so we'll start now. I think the attendance will grow over the time. So, sir will talk about today mostly on the security assertion based verification. So, initially we'll start with what is basically assertions and what is the security assertions, and then it will build up over the day. Thank you.
Good morning. We are going to talk about trust verification using security assertions. So, the concept of before I talk about verification of security verification, I want to make sure you have the base for what is validation verification, and I am going to zoom into that aspects. Once we are done with that, then I am going to talk about security verification, and then I am going to answer 2 fundamental questions, which is if everybody knows all these problems are there in the world, why do not they design things that can withstand all these vulnerabilities? Why do I need to verify? So, I will answer those questions, and then I am going to show how do we verify using assertions. You can verify in many ways, and how do we verify assertion and how that fits into the big story. After I give a little overview of validation and verification, you will get an idea that assertion based verification basically fits into the simulation based validation. So, what happened to the computer? Actually nothing happened, nothing happened. This can happen. So, the key idea is getting a blue screen pretty much freaks out anybody except one set of people. Anybody knows who are these people or the engineers who actually becomes happy when they see the blue screen? Not the attackers, attackers of course enjoy it. Anybody has any idea?
I think those who are not interested.
Yeah, those who want to take a day break and don't want to have class. No, apart from that, so I will briefly talk about post silicon validation. When you fabricate a chip, it comes to the company, you put it on the board, put the operating system and you expect it to work. Most of the time we do not even get anything in the screen, and it is like that freaks us out. So, we have to do exactly when you write program, the way you comment one of the function, comment another function until you start it printing something instead of giving error. We literally had to kind of turn off, think of motherboard, all the chips are there, you have to literally turn off power supply to each of these selectively until something comes on the screen. So, blue screen actually does not freak me out. Many people are scared of ghost, I actually want to see a ghost. So, the idea of verification boils down the fact that even simple bugs can cost a lot. So, here is a tiny example of a software bug, and as silly as a conversion of 64-bit floating point number to a 16-bit signed number, that conversion there was a tiny bug in software, and that led to $7 billion in 1996. That is about 10 to 15 billion. So, a tiny error by a software programmer cost that much. So, it is not just in software, even in hardware, a tiny bug in floating point division. If you recall, in FPGA we talk about lookup table, floating point unit is implemented using a lookup, not FPGA lookup, but just a table lookup, and in that lookup there was a mistake. So, lookup table was populated with some values. There was a mistake Intel did populating that table, and nobody would have ever found out until this professor, it is not me, professor spent all this formal verification time and effort to figure out are there any scenario where this may fail, and found that scenario, and that costed Intel 475 million in 1995. If it was not for Intel those days with deep pocket, any other company would be out of business, and it is a brand name issue. So, any tiny bug, and remember in a bigger scheme of things, billions of transistor, think of one transistor was wrong, with one table, one entry, there was a wrong populated table. Now, it is not just software, hardware, even operating system has a problem. So, this is basically Mars Pathfinder, this is the not the last one, it is last to last one to visit Mars. And when this dude landed in Mars, it wanted to fly. This solar panel you see on top of it, it was opening the solar panel and closing the solar panel, opening the solar panel, closing the solar panel, as if it wanted to fly. And you realize that anytime anything goes wrong with US infrastructure, they think Russia, Iran or China is trying to hack. At least in this case, none of those were happening. If you have taken operating system course, if you know the notion of priority inversion problem, and in a silly example I can explain it to you. So, let us say this is one of the, choose one of the train station, my favorite train station Howrah, and the bathroom is very problematic, and there is one room, one door, let us say one door, and let us say I entered and locked it. And now, choose a person who is higher priority than me, Prime Minister of India, waiting outside, very higher priority, significant higher privilege, but until I unlock from that room and get out, I am more powerful than the Prime Minister for that time. Of course, you can imagine breaking the door and all that stuff if you ignore that. So, that is the scenario happened. There were 3 tasks, 3 programs, think about it, 3 programs running, task 1, task 2 and task 3, and task 1 is higher priority than task 2, which is higher priority than task 3. And what was happening, that the task basically 3 is basically it executed a semaphore. If you have studied semaphore, it executed a lock. Think of that bathroom and closing the lock, and task 1 comes in. Ideally it wanted to preempt task 3, so the task 3 stops, context switching happen, task 1 starts running, but because it got the lock for a mutual exclusion and these two operates on that data mutually exclusive data, task 1 had to wait. In between task 2 came in who has nothing to do with that shared section, and it basically continued for a long time. Then control came back here, then this one executed unlock, and only then this one got, this would have got the control. And there was a security mechanism in that, that when this data collection is happening, enemy countries of USA or not friendly countries of USA should not steal it. And because this task is a highest priority task and it takes only let us say 20 millisecond, if within 30 millisecond or whatever 1 second it does not terminate successfully, system will shut down as if somebody is stealing something. That is what was happening. It opens the wing, wanted to transmit something, but in the meantime this task 2 comes in, one of the communication tasks which has nothing to do with the business, but because of this precedence and all that, this is called task inversion, priority inversion. You become king for a day because you can block the king, right. Now, fortunately the problem was solved as soon as they figured out. Operating system also has a concept how to solve it. If somebody blocks a higher priority task, at least for that duration until it releases the lock, it becomes higher priority or equal priority, T1 equal to T3, higher priority than T2 for that time frame. So, therefore, in that case T2 will try to attempt to take the control, but T3 for that moment is higher priority. Control will continue, it will do the VS and then control will go back. So, this flipping thing. So, priority inherent switch, they turn it back. Now, this is technically not a bug, solution was there before Mars Finder was sent to Mars, they forgot to enable it. But the point I am trying to make, I took only 3 examples just to illustrate the point, whether it is a tiny software error, tiny hardware error or even tiny operating system bug or forgot to set a switch, it can cause havoc. So, now before I talk about verification, we talk about hardware, software, firmware. One of the chip most people focus on is this system on chip, we call it system on a chip, and it basically have a typical automotive SoC would have around 100 to 200 component, and each of the component, major component is always a processor, then there could be voltage regulator, bridge and tons of stuff, controller, adapter, lot of different types of memory depending on the system, and this is kind of the peripheral bus and all these are standardized. So, that you can buy, you as a system designer can buy components from multiple parties and put on the bus, right. So, this is the kind of chip, and if you look at the when different companies chips look different. So, if Qualcomm is building their chipset or Broadcom building their chipset, Samsung, Apple, they look different, but if you take the summary of it, this is the summary. Half of them fail the first time. So, you design something, send it to the fabrication facility, bring it back to your facility and test it, it does not work. It does not even give a blue screen, it just does not work. So, that we call as first silicon failure. And if you look at the first silicon failure, the scary part is half of them fails. If you look at those half of them, out of half of them, how many of them failed, for what reason? This is a worldwide story. Some SoCs are tiny, they may not fail that much. Some SoCs are very complex, they may fail more, but this is an average. If you look at it, do any of you see anything funny? So, again let me put the number there for you to kind of understand. So, about 50, oh that line is a next page, okay. About 50%, oh boy I can write 50, sorry say again?
Can you select the pen?
I thought okay let me do that again. Oh, pen was not selected. About 50% fails first time, right. So, let us just digest that fact, which is a very scary fact. Fabrication is very expensive. I can get into the detail. Each fab cost in the order of billions, 2 to 10 billion to build, and they will be obsolete in like 2 to 5 years. So, they have to make up all of that money in that tiny time frame. Like in 3 nanometer technology, the fabs that are running, you have to understand the particle size, dust particle size cannot be bigger than 1 nanometer. So, they have the filtration mechanism, air conditioning mechanism has to accommodate 1 nanometer size particle. So, that is the clean room, that is the most expensive part. People think this photolithography, drawing transistor, sure those are expensive too, but really this whole chemical process of making that clean room is the most expensive part of the story, but not whatever it is 50% fails. Out of that 50%, this is the story. If you add up, this is supposed to add up to 100 unless I made anything wrong, it is supposed to add up to 100. Now, do any of you see anything funny here? So, these are the reasons. So, for example, if I choose firmware, so failure happened because of firmware is about 10% of the chips, 10% of these 40. So, this is 10% of 50%, which is 5%. 5% of the chips failed because of some firmware problem. So, let me start the discussion. That is actually not a scary thing, because firmware patching is easy. You just change the firmware, update the firmware, problem is solved. Anything funny you see in this diagram?
Safety feature and security feature data is pretty limited.
Safety security feature data is limited, that is interesting, because these numbers are 2020, people are not taking them seriously. Anything else you see here? How come the big things does not show up to you? Almost 50% of them, which is 25% overall, is failing for logic or functional bugs. I can zoom into any of them, talk for hours, I will just want to zoom in this for today. Functional error, that means you designed an adder and it is not adding correctly. What would be your first impression? That means you wrote a program, you did not test it and you just gave it to your customer. Do you think that is correct? No, right, that can't be true. So, we are trying to dig in what exactly then happened. Why so many of the failures are due to functional errors. But I want to spell one more thing, delay is not here. When you think of functionality, delay is also important, because what is not correct is that you give an adder and it add 2 and 3, what should be the output? I want to see hands. If you add 2 and 3, how much it would be? I want to see hands. I want to see all hands. I want to create a practice that you guys raising hand. I would have loved to see both hands. Doing exercise is good, it is 5, right. So, the thing is, even if the adder produces 5, but it does not produce in 1 clock cycle, that is actually bug, that is a problem. Why would not it not produce? Because remember, this is not an electrical class, but just to explain, if there is an AND gate, there is a delay associated with, let us say it is a 1 nanosecond. Because of the fabrication technology, because the temperature on which the computer is operating right now, the delay will change, the parasitic capacitance will change, and it is a charging and discharging, and charging and discharging, it is e to the power t over r c. So, it is not like straight goes up, it takes some time to get to the value that we believe as 1, glass becoming full, and that is 1 nanosecond delay in layman terms. And if the temperature is high, it takes longer to charge. If the fabrication is slightly deviated, process variation, then it will not be 1 nanosecond. So, if it is a longer than 1 nanosecond, it is going to take 2 clocks. So, even if it 2 plus 3 produces 5 in 2 clocks, that is not good, that is treated as, because everybody else is waiting for that result. At the end of 1 nanosecond, somebody else reading this value is getting a garbage and is continuing with that garbage, its overall thing is garbage in, garbage out. So, that is not acceptable, right, makes sense. Okay. So, now I am going to zoom in. So, basically this is also treated as a functional bug. In fact, even if which I am not planning to talk, even if power, right, this power thing, dynamic power management, that is almost 30% of the logic. Think of, you wrote a program, 30% of the program is power management, dynamic voltage scaling, all that. If the power management functionality was implemented incorrectly, it was supposed to turn off, let us say a controller, by mistake it turned off the processor, right. So, then it is going to produce wrong output. Your logic is correct, but eventually it will show up as incorrect output. So, no matter what it is going to lead to incorrect output, but I am going to just focus on not these indirect ones, the direct ones, and I am trying to give you an answer why so many of them failed. One of the reason is there any course in IIT Guwahati on verification? There is one. Okay. So, make sure you take that course, because most people, we have this social mindset that verification or testing is a bad thing. I keep hearing engineers talking, oh you are lucky you got into design group. Yeah, I was in testing group. Give me a break. You want to go enter, you do not know anything, you want to start designing and you expect that to be successful. In fact, if that is successful, many companies will use it and they will find bugs, somebody has to fix it, and you do not want to fix it, you do not want to clean up your own mess. It sounds very funny, and you want juniors to fix it, but when you are junior you do not want to fix it. To me it seems like very non-intuitive cycle. In fact, what I will say, company has done enough they could do. In 1995, this is again an average of the worldwide average. So, 1995 a typical design used to be 1 million gates, think of 1 million line of code and 20 engineer years. 20 engineers here you can think of 5 engineer for 4 years or 4 engineer for 5 years, whichever way you, it is definitely not 20 engineer and 1 year, which is now. Now most of the designs have 1 year life cycle, then it would be 20 engineer 1 year. An important part is every design typically used 100 million tests that ran. 2001 10 billion tests, 2017 1 trillion tests, 2024 these numbers are available, billions of transistors and trillions of tests. This number is not available, I just put that in. My finger also does color, nice, this is very good, right. So, that is the story. Now, I am going to ask 2 questions at this point. I want everybody to raise hand. We know 2 things, no, professors are not allowed. We know 2 things for sure, that 50% of the failures are because of logic bugs. We know that. We also know what the industry is doing or industry was doing in 2007, was doing in this. Why didn't they do more? If you knew, if I do this much, that is not good enough, why didn't they do more? So, why did the stop at 1 trillion? Why not 10 trillion? I do not know whatever the next number, gazillion, whatever it is, why didn't they do that? You can run in cloud, it is not that expensive, and of course, it is all relative, right, cost. Would you be paying $500,000 or $1 billion for fabricating second time, or would you just take some cloud resources, use 100 or 1000 more computers or million more computer for few days, and that would be much cheaper. Why didn't they do it? I am expecting all hands from the students. I am seeing only one, I am not happy. Go ahead.
Sir, one reason could be that they want to shorten the life cycle because of the competition part. So they try to push in the product and then eventually give out the patches so that they can kill the competition.
Okay. That sounds good, but did any of you realize managers always get paid more? PhD students always do the work, professors always get paid more, they get all the awards, all the recognitions. Didn't ever bother you? It always bothered me, in industry. I do all the work, and the people who have tea with the bosses, they get all the salary hike, and that actually true even here. First of all, managers are incompetent, take it from me, tell it anybody, they are all incompetent people get promoted, because they have time and energy to do the necessary oiling to get promoted. And then what happened? All they do, every company you go, that is all they do. They plot over the time, let us say in last week, last day, how many bugs were found, they plot, and let me tell you how fundamentally flawed that is. And plot would typically look like this and stuff. I did not make it 0 because even if you did not find any bugs, that does not mean there are no bugs, right. So, I will get into this plot. The fundamental flawed problem is, first of all, people are reluctant to report bugs in their own design. they will just fix it and forget about it. That is one story. Second is, if you are not finding any bug and your boss is manager is pushing, please give me a thumbs up so that we go for next stage, layout, fabrication, and then there is all these pressure from the customers, when are you going to give it? So, there is all of that stuff. But then the bigger problem is, even if you ran lot more computers, let us say you used 1,000,000 computers and there is only one bug, it will fail in all 1,000,000 of them, and depending on who is running it, from operating system guy, processor guy, the programmer guy, it might, the same bug will show up differently in different places. So, we need 1,000,000 engineer to debug them, and then eventually we will find it is the same bug. So, that is not possible, that is simply not possible. Just the ability that I can run million or trillions of test case and trillions of them, and when it fails somebody has to analyze it. We do not have that manpower, computer would not do automated analysis for you. So, that is a real problem. Now, let us come back to this manager's dilemma problem. So, if manager is not seeing anything, what is supposed to do? Then they go by statistics. Statistically, last year my competitive companies, everybody did this much, last few few product generations we did this and we were fine, we will be fine. Literally that is to do, and just for between you and me, manager also do not plot this, their secretaries do. So, it is not actually clear what managers do in these companies, get all this money, right. They will make you form all these TPC report, they will force you to go to certain meetings, and when you realize, then come for PhD. Before that I want you to get that pain, because I am not able to convince you academia is the right thing for everybody doing research. So, now let me ask two questions. Now that you understood what I said, why this bump happened? What does this bump mean? Number of bugs in a particular day or a week suddenly gone up. What does it represent? Nobody is raising hand. It basically represent all the components are now working, they are talking to each other, and that interactions basically produced a lot of bugs. So, when I am designing an adder, Dr. Karfa is designing a multiplier or operating system, each of them are fine, but when you put them together, their interactions, whatever stuff, that kind of opened up certain bugs that was not otherwise possible to see, right. Why did it go down? What does this point represent? You found the bugs, you fixed them, of course it will go down. Why did it go up, whether this one or this one? Why did it go up? If it gone down, it is supposed to stay down or at least oscillate right there. Yes, please. Who was saying?
Because that patch may also have vulnerability in that.
Two things. One is the bug fix might introduce bug, but most of the time, based on my experience, bug fix actually exposed some other bugs, which was earlier getting, let us say, going through AND gate, one of them was 0, because one of the line is 0, this was getting masked anyway, because output is 0 no matter what. Whether this one is supposed to be 1 or 0, it will mask it, but this bug fix actually exposes certain other bugs. But whatever it is, that is the problem. So, bottom line, these functional bugs, it is not because nobody was doing anything, because people were doing whatever best possible, and that is one of the reason people do formal verification, which I will introduce in a moment. By the way, anything I am talking about, all of them are applicable for security verification. I will formally bring them back. So, verification complexity for SOC kind of domain, SOC firmware hardware domain is 70%. So, that actually would bother you. Why in computer science, at least IIT Guwahati has a verification course, many departments do not even have a course on verification. So, that would bother you. If 70% of the world story is verification, why it has less than 1% representation in the story, but that is not for us to decide. But to understand an adder, if each of the line is 64 bit, can anybody tell me, it is a 64 bit integer, how many test cases do I have to try to completely verify this adder? Hands please. If each input is, if you are still blinking, let me show you an analogy. This is an AND gate, I have two input, each of them is 2 bits. How many inputs are possible?
4.
How did you get 4? Who said 4 on this side? Yes ma'am, how did you get 4? 2 into. So, there are two possible choices here 0 and 1, here is two possible choices as 0 1. So, you basically 2 multiplied by 2. So, that is how we got 4, or we can view it 2 to the power 2, right. So, 2 to the power 2. Now, sorry, let us not go into 2 to the power 2, it would confuse. Okay, so, 2 times 2. Now, anybody help me out here, how many possible inputs are there? 2 to the power? No, 12 will not work. 64 is each of the 64 bits is each of the input. Anybody else? No, professors are not allowed. Anybody else? 2 to the power? So, there are 2 to the power 64 possibilities here. 2 to the power 64 possibilities here, here is 2 to the power 64 possibilities here. So, then this will be multiplication of them, all possibilities of this. So, then total choices are 2 to the power 64 multiplied by 2 to the power 64. Can anybody help me, how much is this? 2 to the power 120. I like that, but you started with 12, but what happened to the 8? You forgot 2 to the power 128. Can anybody tell me what it is in 10 to the power? So, you guys 32, how did you get that number? God, 2 to the power 10 or about 1024, which is 1000, is about 10 to the power 3. So, you do not need to be a genius to figure that out. 1024 is about 1000. Anyway, so I am not going to clean it. So, this is around that number 3 to the power 10 to the power 30. I want you to take a blink and think 10 to the power 12 is a trillion. There are about 200 billion trillion stars in the universe. This number is much larger than that. Even all the computers in this world running forever will not be able to try all possible inputs for an adder. Just verifying an adder completely, all possible scenarios. And that is where the question is, if verifying an adder is impossible, what is the hope we can verify an arithmetic logic unit, which is an adder, subtractor, multiplier, divider. If I can't verify that, what is the probability I can verify a processor? If a processor I cannot verify any systems, even in the airplane we fly or a car you drive or the phone you use, do not even think about it. I can assure you the airplane you fly or I fly, 99.999% of it is not verified. Now comes the interesting question, I want all hands here. My chances of dying in a lightning strike when I go out of this building is higher than dying in an airplane crash. So, airplane is that safe. How can you explain a device with millions of lines of code not verified, nothing is verified, it is completely bogus thing, has so much reliability. How can you explain this? Absolutely garbage, but huge reliability. And in fact, most safety critical systems have huge reliability. How come? So, if I draw a, if you know Venn diagram, if I draw a Venn diagram, if this is the space of all possible scenarios, it is probably a tiny here, maybe little bit there, this is all verified in a airplane, that is all is verified. Up to the, it is still not up to the scale, very tiny kind of scenario is verified. How come it is still so reliable?
So, probably because they have priorities on which test cases are most important and hazardous. So, they run those in first.
Absolutely. So, I am trying to involve everybody. Why is it a rocket science to you to answer or participate in this discussion? In fact, one of the danger you are doing to yourself, most people say, oh, it is a rocket science, you will not understand. Rocket science is actually trivial. If I teach a class on that, you will figure out it is trivial too. It is just that some community of people want to keep their ego boosted and they say, oh, this is very complex, and you are supporting them as a social engineering. You are falling in their trap by not participating in this discussion. Please participate. What would be the wrong? You will give a wrong answer. It does not matter. you want to push forward and become famous, right. So, the way you do is participating and brainstorming. So, the reason it works, before I go there, let me go to the Apple's philosophy. Adder verification is not possible. Intel still tries to verify all possible combinations in a processor in some manner. I will show that when I talk about formal verification. Apple said we do not want to do that. It is not possible. There are bunch of processor, bunch of memory, billions of lines of code. There is no way they could be verifying rest of the lifetime of the universe before releasing a phone in the market. What they do, they give hundreds and thousands of phone for free. And those phone, those people, they will pretty much use for anything like drinking, driving, smoking, texting, they will be doing all that type, calling, voice calling, multi people calling, people will be trying everything possible. And whichever people complain and say this is mistake, that is mistake, they will fix it and refabricate it. Apple is only one of the few company who do not care about a half% silicon failure. They do multiple fabrication before product release. They just release, instead of verify a lot, almost done, then fabricate, they immediately fabricate, find all the bugs on the real device, because then you just verify the application scenarios. If the device was not ready, you cannot ask a stranger on the street, can you come sit in front of the computer, fold your shirt and then try finding some bugs? Nobody would be interested, but if you give somebody a phone, try different ways of using it, everybody would be interested. Even kids like Om would be happy to find some bugs, try different things, play with different way, because once it user friendly, lot of people will try. And if you can cover 99.99% of the use cases, other cases does not matter. Even if somebody complains, oh my phone is not working, this and that, it is much cheaper for the company to give them a new phone than doing all these verification and basically still not feeling bad, I did not do enough. Any questions? Please participate. I am putting my best foot forward. I want each of you to do that same as a respect to me.
Sir,
Yes, please.
One question.
You
from
made me
my
happy.
side.
Go ahead.
When we are talking about security perspective, basically in GRC, there is a concept of risk management in which we analyze the risk, and based on some metrics we put forward our decision. Either we have to avoid it, transfer it, or we have to mitigate it. So I am thinking in that way. Many companies do not do verification on a large amount because they know that the risks which is coming to them has not been that much higher
Compared to if you spend energy,
compared to
absolutely,
that.
absolutely.
So they basically avoid the patching at the earlier time, and after releasing in the market they came up with the feedback, and based on practical approach they are patching the system.
Absolutely.
That is much convenient for the company and
Absolutely.
much convenient on the user side.
But we can't do that for airplane.
Yeah.
Airplane is flying, something went wrong and then you are patching on the flight, that is not going to happen. That does happen once in a while, and there are 3 incidences where the landing gear did not engage, actually did engage, but the tire supposed to be this way, tire became this way. So, if it lands it would keep rotating, an accident. So, the mechanism is, it is all well known thing, you have to keep on flying to burn the fuel, or you have to somehow open the fuel tank and release the fuel down. So, it is going to do crash landing. If fuel tank is on, it's everybody will die. If fuel tank is not on, the explosion will not happen, some people will die. But anyway, that is a different story. So, the reason airplane or any safety critical systems, all the use case scenario that is possible, that they exhaustively test, engineer test, company test, then Federal Administration Aviation requires that there is a third party, independent third party with whom you are not having tea and coffee, they will do their evaluation. So, there are multi-layer of evaluation, all the use case scenario, that is how it works. I am coming back to the story now. So, typically there are 3 scenarios. Dr. Karfa yesterday talked about manufacturing testing. So, many companies, there are thousands of engineers, they are just focusing on manufacturing testing. Most of the energy people try to put on the before things get fabricated, because it much faster to fix, less expensive, but after fabrication there are two community. This community believes it is functionally correct, there could be manufacturing defect. This community believes there are no manufacturing defect, there are functional bugs, but you realize both can happen at the same time. A manufacturing defect will show up as a functional bug, a functional bug may show up as a manufacturing defect, but we will not get into that philosophical discussion. So, verifying as early as possible, capture as many bugs as possible is a good thing, but verifying at this level has one good thing, everything bad, one good thing, actually two good things. One good thing is you are actually testing the real device on the real system. If you build a robot, robot is actually working. So, there is one more good thing about testing after fabrication, very powerful advantage. Any of you know? Yes, please.
Sir, basically when we are making a project, there are several components. We try them individually, but when we are integrating them, then the deployment may not be that fruitful or may be diverted from the actual result. So testing at the time of integration and after deployment is the real use case that we are providing to the customer, and we are basically testing the software
Real
on
product.
practical reviews.
Thank you, thank you. So, that is the first one I said. Second one is it actually runs at speed at gigahertz. You can run a test kit at gigahertz, this typically runs in megahertz, because that is typically simulation speed. So, create a scenario. So, for example, if you can find a bug at a gigahertz speed for few seconds, that will take almost a week to run on a simulator to reproduce or fix. So, you have a strategic advantage that you can run at gigahertz any testing you want to do, but the problem is the amount of trace it produces, terabytes of data. How do you manage? That is a different problem. So, I will skip all of that. Post silicon I talked about.
This pre-silicon has one more advantage of observability, right? So this has less observability.
Pre-silicon also has the advantage of observability. Even if million lines of variable, millions of variable, you can put a printf, although that is unmanageable. But here, as we talked about, the trace buffer is very tiny, 128 or 1000 signals for 1000 cycles, right. But now the security perspective I want to give you. So, most people in this world have low IQ, take it from me. They will always do bulletproof door, bulletproof car, they do all of that stuff, and they have a significant vulnerability. They are addicted to drinks, drugs, many other things I am recorded, I can't tell you. An attacker would attack at that point. Why would they try shooting at the bulletproof door when you are surrounded by 200 bodyguards? Why would they do that? That is stupidity. Why would I come to your house and try breaking your bulletproof front door? I can break your bathroom door, sure it would be smelly, but my objective is not to get a good smell, to steal you, to rob you. So, I will break your bathroom door. So, breaking through this is analogous to breaking your bathroom door instead of trying to come through your front door. And it is not just in even in USA, all the front doors, everything so exotic, and whole house is made of glasses, and I never understood, I do not want to understand, but I am just saying it is an attacker's paradise, everything. So, now let me zoom in to little bit of validation verification story. What are the underlying principles that makes it happen? But before that, I want to ask you a question, because if you guys are not answering, I will fast forward. So, you have two things in the context of verification. One we call as specification, something that is given, something we assume as correct. So, whenever your professor gives you a project description, the English document, that is your specification, and when you implement your project, that is your implementation. And in English, if I have to kind of talk about what it is, does implementation satisfies the specification? That is what we are trying to. A verification basically means whatever you implemented, does it satisfy the specification? Assumption is specification is correct. Many times it is a important legitimate question, how do you know specification is correct and who corrected it, how did I verify it, because nobody else to compare it with. Let us not discuss that today, we can discuss that offline. Let us assume we have a model that we know as golden. So, when I do 2 plus 3 and expect a 5, the golden model is in my mind. Somebody told me 2 plus 3 is 5, or you can think of this could be a C program and this could be a RTL, some gate level, some kind of hardware description, language description, detail, or it could be RTL, this could be get implementation after synthesis, this could be C program, this could be assembly. So, whichever way you look at it, or the first one could be C, second one could be C by running through Professor Karfa's the tool that insert the masking logic and all that stuff, security aware implementation. So, functionality did not change. So, we are trying to see does implementation satisfy the specification. In this context, I am going to ask you a question, I need some space, or W will work. So, in this context, which one is true? I implementation is equal to specification, I is a super subset of specification, or I is a superset of specification. You have to raise hand at least for one of them, and please say which one you believe. One, how many of you think when I say implementation satisfies specification? Let me write it for you. This is the context. Implementation satisfies, does implementation satisfy specification? That is really the verification question. How many of you think 1 is correct? I have one hand. How many think 2 is?
Actually, I am going for 2.
Oh, no, wait. 1, raise hands. Nobody. 2, because in my class when I ask, I have 300, 400 people classes. Before people raise hand, they look left. It is good that nobody is looking left and right. 2, 1, 2, 3, 4. So, this is 0. Here I got 4. I will add up. You know, I know mathematics. I will add its total number 3. 3, 2 hands, 3. It does not add up. The number of people in the room is 20. 4 plus 3 is not equal to 20. So, let us try asking those of you said implementation is a superset of space. What is the rationale? 3, how many of you raised hand? Explain to me.
Sir, with the simple notion that if implementation should at least be equal to specification. So, it can give me more things, more features or more capability, but at least the specification part should be there in the implementation.
Okay, who else raised hand for this one? Yes, what was your rationale for choosing this?
I think the same, the implementation could be more than just the specification.
Okay. So, most of my students answer always give implementation is this big and this is implementation, specification is this small and tiny. So, therefore, this relationship holds. If I did not give anything, this argument is fine. If I gave this, I satisfies S. In the master slave model, who is master, who is slave? I is trying to satisfy, make happy S. S is the master, I is the slave. How can I be more important, bigger? So, this is not an answer. Equality, we are trying to go there, this is the correct answer. So, let me get into this relationship. So, let us take the adder example, it is easy to understand. If this is the whole space of adder, you already know some adders, right? Carry look ahead adder, ripple carry adder, half adder, so many of these adder, and then the question mark means there are other implementations adder algorithm possible that has not been invented yet. So, it is a huge space, but the one you implemented, let us say you implemented ripple carry adder, but even then it does not cover the whole space of this, because this one says ripple carry adder of anything. Remember, specification is C equal to A plus B. When you say A plus B, first you did not say it is a ripple carry adder, you did not even say it is a 32-bit addition, you did not say it is a integer addition, floating point, you did not say anything. So, when you do not say anything, it actually from a verification context, it represents a bigger space. But implementation customized everything, it is customized to ripple carry adder, then it customized to 32-bit, and it probably customized to integer, 2's complement integer. So, it is a really a tiny scope you implemented, and that is why, and tiny scope you are verifying, and you guys arguments about it might have more. It's from a social engineering perspective, it makes sense. Your customer asked you to implement something, you implement more, it's great. From a verification perspective, it's a bad idea. From security perspective, it's a very bad idea. It should have nothing more, nothing less. Anything more means that's the funny thing, probably an attacker's malicious implant, right. Any questions? Verification is actually very interesting if you kind of put your mind to it. Now, there are two ways of verifying: simulation based validation, which is I am going to subsequently talk about whole day. Assertion based validation is one of them. There are many others, and simulation all of you do, right. When you implement your project, you do simulate before you submit to your professor or teaching assistants to review it, right. So, this most of you do. So, I am not going to spend any more time on simulation based validation except some comparison. I will spend little bit of time on formal verification, so that you kind of see what that is. Simulation, you can simulate any size design, whether it is a million line design, billion line, it may take a long time, but you can. But formal verification you cannot do. I know I did not talk about it, what it is. It is a mathematical proof, it gives you a guarantee, complete guarantee of verification. How, what, I will zoom in a moment. Simulation does not give you any guarantee. Remember the adder, we can't even completely verify the adder, there is no guarantee. All you can say, I did my project and I ran 2 test cases and it worked for those 2 test cases, that is all you can say. But formal verification does not care about inputs, but it cannot deal large designs. So, that is why company always applies to small and critical components to completely verify, like cache controller, floating point unit, if you want to do adder, because those adders also important in cryptographic algorithm or some cryptographic functions, because those are security, like bodyguard, you want to make sure your bodyguard's body is strong. So, all these cryptographic algorithms, those they completely verify to guarantee. Now, I have a question, again I am expecting all hands here. To me it seems like both are equally bad, both are bad persons. This does not give any guarantee, this cannot run large designs, but company have large designs. So, as far as I am concerned, both are useless. How many of you can say what I am saying is wrong? What I am saying is wrong. Both are not equally bad, you have to prove to me both are not equally bad. They are bad in a complementary way, which is they help each other. Yes, please.
Sir, I think that they have their own merits, such as the validation, the simulation based validation that can be done in a real life scenario with the hardware and actual practical.
Let me pose the question again, I know where you are heading. So, I am dealing with 64-bit in adder, I do not want to deal with 64-bit adder, I want to deal with 2-bit adders, right. So, then I have a tiny design, only 2 bits, 4 scenarios, I can try all these scenarios. So, I have complete functional guarantee using simulation. This dude is also guarantees only small designs. So, to me both are equally bad. I am playing devil's advocate,
Sir, but
you have to correct me. This is also can guarantee for small designs, this also can guarantee for small design, both are useless for real world.
But sir, after the implementation has been carried out, I need to do a validation of that using simulation based. Formal verification is on the paper, what I understand.
No,
So-
formal verification is also not on the paper. Okay, so let me say the bottleneck of this one, let me write it for you. Input space complexity, number of inputs, input space complexity is the problem here, and this is design space. Think of finite state machine, state space complexity. This one does not care about inputs, how many inputs you have, because it does not simulate, but the state space, think of a finite state machine, how many states, state transition, unrolling, all that stuff. So, theoretically you can have a design which has a lot of inputs, but very tiny state space, then formal verification is perfect. So, they actually complement each other, that is what industry uses, and that level of understanding is enough for rest of the day. Yes, please.
Firstly, I will ask you a question.
You should start answering my question before you keep asking me questions. Go ahead.
So,
Go ahead.
why do you think in large scale formal verification will not work?
Because as we go along, you will see how formal verification work. It creates the state machine, and then keep unrolling the state machine. So, wait for until the break time maybe, or maybe we will start right now, it will answer that question, how it operates, what does it do, then you will understand. Any other questions before we proceed? Okay. So, now that we understood about simulation based validation, I am going to skip all of that. Think of your project, whatever tests you generate and all that, I am going to skip that. Formal verification, there are many. I am going to just let me try in 7 minutes 7 techniques. There are, so my objective is not to get into the detail of any of them, and in fact, just model checking is a full semester course in University of Texas at Austin. So, I will not even attempt to give you clear idea of what this is, it is just you get a rough idea what does it do. And the inventor of model checking actually got the Turing award, 3 of them, and that is treated as a Nobel Prize in computer science. So, each of them is, and also SAT solving, those of you are from algorithm area, you know, is such a powerful thing, you can use it everywhere. Not only that, complexity theory people, whether they try to map satisfiability problem into that problem to prove what is the complexity of that problem. So, these are all powerful things. Let me just walk you through, so that when you next time hear that word theorem proving, you kind of know what the hell are they talking about. So, theorem proving, I will take a silly example. So, we have a set of rule, father x y, meaning it is a parent and x has to be male, right. So, if I give you a set of rules and then I ask you a question, is Bill uncle of John, that is yes, if I can't even see Sue is uncle of John, that would fail. And the way theorem proving works, and you guys have done all of this unknowingly in your 8th, 9th, 10th grade, you probably prove that left hand side equal to right hand side. Most of you start with left hand side, keep going, and then you eventually say right hand side, and hence the proof. Or before I do, let me ask, how many of you can prove a plus b whole square equal to a square plus 2ab plus b square? You can come here and prove. How many of you can prove a plus 2 plus 3 is 5? Okay. So, this is theorem proving. You start with somewhere and you try to prove something, and in this particular example what will happen when you ask is uncle Bill of John, that is a node you have to prove. To prove that, go to the rule uncle x y, meaning you have to prove a rule called parent, then you have to prove a rule called sibling, and it is a add and operation, you have to do all of them, and then you have to prove a rule for male. And as you can see, male x, this is Bill, what did I do? This is Bill, and let us see somewhere it says Bill, male is Bill. So, this one is true. So, you keep on breaking each of the tree into subtree, when all the leaf nodes would be true, then whole theorem has been proved, right. So, it mathematically breaks down the problem into sub problem, then prove those sub problems, and that is the theorem proving. It does not care about the input at all. Now, you might be saying, well, all this stuff, first of all, there you can download a theorem prover, it comes with this example, you can play with it, and I gave a silly example, but in real life if you designed a processor, let us say RISC-V processor or a version of RISC-V processor, if I asked you, can you prove that this has in order execution, before I prove, can any of you give me an English sentence to spell out how do I write the theorem? Proving is later. What are we trying to prove? In order execution is the word I gave. In an English full sentence, can any of you tell me what exactly I have to prove? Before we convert that to mathematically, give it to a theorem prover. You give the design and the theorem. So, you give the design, and if I can formulate this as a theorem to the theorem prover, and theorem prover will basically either say yes, theorem is proved, or say nope, here is a example, we call it counter example, where it fails. Then you can, a designer can take that counter example, try to fix the design. How do I write this in order execution? Yes, please.
In English, sir, I am trying to prove that root left right is the sequence of execution.
Okay. So, if I spell that in English, non-English, if there are two instruction II and IJ, any two instruction, randomly separated by random delay, then if this is the case, then I am going to say in this particular context I am going to say the start time, if start time of I I is less than start time of I j, then the end time of I I should be less than equal to end time of I j. Then if you give that to the theorem prover will prove it for you. So, the theorem proving problem is theorem prover is very robust these days. It may stop once in a while and you have to say, oh, did not you know for integer additions 2 plus 3 is actually 3 plus 2, the kind of associative rule applies. Sometimes theorem provers get confused, you might have to put some lemmas in there, some stuff that it is supposed to know, for that context, that scenario it does not know, you have to provide it, right. So, this is basically theorem proving. Mathematically it proves it, deals with bunch of equations. So, this design would be converted to bunch of equations or formulas, theorem would be bunch of formula, it deals with that formula, and basically what the way it constructs that tree and too many subtrees. Now, going back to your question, because it is constructing the tree and the scenarios, if the design is complex, the scenarios are complex, that scenario tree would be so big, it is not going to fit into the memory. We call that state space explosion, and this will be even more clearer when after the break we talk about model checking. We stop here. Thank you.
So we will have 30 minutes break now. We will again assemble at 11:30.
हाँ So why mathematics people are going from this?
बोला नहीं सब
एक मिनट Yes.
So just to kind of give a reminder that tomorrow we are going to enjoy Holi, right? So you participate in hostels, they enjoy a lot. Okay, so be careful with it. Okay, and so we'll shift the plan to Sunday, but I know Sunday is holiday for everyone, so we try to squeeze the time. Okay, so what we'll do that, we'll have lunch here. Don't expect a very spicy lunch, please. School is better. So don't expect Quasiland, but we'll have something, right? We use a budget constant, right? So we not given much budget to give you lunch every day. Otherwise, I would love to give you. Okay. So what we'll plan on Sunday is like Sunday first half is as it is. 12:30 we have lunch, but we will not make 2 hours lunch because lunch is here only, right? So we'll maybe maximum 1 hour lunch, and we will start immediately. And second half we will not have a break. So I requested professor to squeeze everything within kind of 1 hour, 2 hour, 1.5 hour, and then we'll end there without any tea break. So if we start say 1:30, by 3 we will wind up, maximum 30. Okay? We will not extend till 5. So that is the plan. Okay, sir.
Good afternoon. Today we are going to talk about different types of formal verification techniques. In the previous lecture we looked at how theorem proving can help. Now we are going to quickly look at how SAT solving would be helpful. The idea of satisfiability basically mean if you are given a set of expression, in this example these are Boolean expression, then can we find assignment to these variables so that all of these expressions are true. So, for example, if you give it to a SAT solver, it will come up with A equal to 0, B equal to 1, C equal to 0 and D equal to 1. Now, just by looking at it, it may seem like, oh, who cares finding SAT assignment. As I go along, you will see this is useful everywhere, anywhere and everywhere. If you want to solve, if you want to play with SAT solver, and there are many SAT solver, there are conferences, SAT conferences, but I always put this one because this is what I learned first, but as you realize this is more than 20-year-old. So, what SAT solvers again is the same thing, it takes the design, takes what you are trying to prove and then construct something called conjunctive normal from and proves it, mathematically proves it. Now, the most widely used one that Professor Karfa teaches in GIAT Guwahati also is the model checking. This is widely used as a formal verification technique for verifying functionality, security or reliability, any types of guarantee, real time guarantee, thermal guarantee, power budget guarantee, people all use model checking. And the basic idea is very simple, you give the model which is the design that you are trying or implementation that you are trying to check, and the specification in that context which is the property you are trying to check. Think from a traffic light controller, let us say one of the scenario you want to test, both side of a traffic light controller should not be green at the same time. If that is what you want to write, the traffic light controller design you have, the VHDL, Verilog, whatever language you wrote, and the property you write, both sides should not be green at the same time, you provide, and then model checker will check your implementation and either say yes, the property is satisfied, it will never, this problem will never happen for the lifetime of that system, or it says yep, here is a sequence of event, a car waiting, a pedestrian press the button, another car waiting here and both sides will become green because of a mistake. So, then you get that counter example, designer can use it to fix the system. And now I want to show you how, so basically property checking in the back end, it constructs something called binary decision diagram. The expressions you give, it constructs the diagram, and depending on the number of variables and the possible values, it can become, or the interactions of those components can become exponential very quickly, because you are not trying to solve it for one clock cycle, you are going to solve it for either next million clock cycle or for eternity. And that unrolling of that binary decision diagram, you can already see for 2 possible values what are the values of B, for 2 possible values what are the values of C. And then if you think about these, unroll for all possible time steps, it is going to be huge, exponential, and that is where the state space explosion will happen. If you want to think little bit more layman terms, if this is your state machine, and you are doing state transitions, every possible place you have so many possibilities, and then think about somebody who is checking for you, really walking through all possible path and trying to see in any state is there a violation. If there is, it found a state there is a violation, then it will construct a counter example from there to all the way to start state, and that is going to be the counter example. So, possible states after unrolling is really the state space explosion. Now, binary decision diagram, this exponential nature can be controlled in a specific scenario, where you do not want to prove for eternity, you may want to prove for only next time step. If a car is waiting, within 10 seconds it should get a green light, let us say you want to give that guarantee. Any kind of bounded guarantee, we can use the notion of bounded model checking, where satisfiability would be helpful. I am not going to get into the detail, but simply saying that if you know the initial state or the equations or normal forms, if you know the state transitions for, let us say this particular example for k cycles, and you write the negation of the property you are trying to check or the behavior you are trying to check, and you give it to a SAT solver. If SAT solver can find for an assignment, so then basically that assignment itself is the counter example. Why? Because we are giving the negation of it here. So, this is kind of for a scenario that is bounded, then you can quickly use SAT solver to do model checking, and this is known as SAT based bounded model checking. Now, let us talk about equivalence checking. So, equivalence checking is actually in security case, it is actually very important, because what you want to do is that you want to prove that your implementation and specifications are equivalent, and there is nothing more, nothing less, so that no malicious implant got in. Think of a diff operation in a Linux environment or Windows, you are doing a diff and there is nothing extra compared to that, but as you realize there would be extra, even if your specification and you did a synthesis, if you did a synthesis, it is going to look different and there would be different stuff, and that is going to be a problem. And in fact, equivalence checking can also be done using satisfiability solver. You take the specification, take the implementation, put an XOR gate at the output, give all of it to the SAT solver. If the output is 1, can anybody, let me ask, if output of this 1 given to a SAT solver, what does it mean? How many of you think that means the designs are equivalent? How many of you think designs are not equivalent? Why do you think designs are not equivalent? Thank you. If for XOR output to be 1, either this is 0 1 for a scenario or input, or this is 1 0. So, these two input has to be different. For these to be different for a same input, that basically means they are not equivalent. First of all, equivalence checking does not take any input. I just for the sake of illustration showed this, but it simply means there is a input, there is a possible input for which output would be different, that means they are not equivalent. Now, in general, equivalence checking problem is a hard problem. So, sometimes people map it to a different domain. If you cannot solve a problem in Boolean domain, you map it to polynomial domain. So, instead of binary level you can think of doing word level, and polynomial domain there are a lot of interesting properties. So, polynomial domain, for example, division operation is nothing but subtraction. So, then you have your implementation polynomial, specification polynomial, equivalence checking is basically you are subtracting. If you have bunch of polynomial, you keep subtracting until you get a 0. If you get a 0, they are equivalent. If you do not get a 0, that is a good news too. If you do not get a 0, so for example, you got let us say A or B, that is the remainder. That basically means all possible values of A and B that would make it non-zero, these two designs are not equivalent for those. So, in this particular case 1 0, 0 1 and 1 1, these are 3 possible test cases that would activate the bug or the difference. You do not know whether the design has a bug, but this method will give you a test that would activate that bug, guaranteed to activate the bug. Actually, it does even better. If you have a design, you give input, it creates a cone of influence where difference is there. If you apply multiple inputs, multiple cone of influence, and that intersection is where the problem is, you can localize and fix it. And in fact, there are frameworks at least for mathematical or cryptographic applications where you can give a buggy design, it will fix it for you, give the design back to you. So, that is the power. Then the last one is basically symbolic simulation, and the symbolic simulation idea is in binary or ternary simulation you use certain number of vectors, like remember we talked about 2 to the power n vectors, but in a symbolic simulation you use only one vector. So, this is kind of a missing link or a bridge between formal and simulation. Name has simulation, but it is symbolic. Symbolic is the formal simulation, it simulates, but it only uses one test to give you the complete guarantee. So, I am not going to get into the detail, but I wanted to introduce you these concepts. Now, I am going to answer the next important question, which is if people knows that there are all these vulnerabilities, why didn't they design so that it can withstand these attacks, right. So, whether you call it countermeasure, mitigation, there are many, but these can be kind of divided into bunch of classes. I wanted to touch upon some of them before I move on to assertion based security validation. So, before I even get into this, what depending on which domain you are looking at, your security objective should be different. So, I am talking about something about communication domain, and we will talk a lot more on Sunday or delved into it. In the security domain, authentication basically means if somebody talking to you, how do you know it is that person? If somebody says I am Dr. Karfa, how do you know it is actually Dr. Karfa? It is not somebody else. How do you know it? Is it the voice? Large language models can fake the voice. Then, so is it his face? Large language model can also fake the face. Then, so that is basically authentication. Privacy basically means if I am talking to you, I do not want anybody else to know or understand it. That is basically the privacy. Integrity basically means that if I am talking to you, other person may not be able to understand it, but they might alter some of my text or binary, so that when it reaches you, you get a different message, right. So, let us say I am sending a message something similar to this, and the really message goes is I hate you, or maybe some symbol will do, right. So, but of course, the alteration has to be smart enough. If you just randomly change bunch of bits, it will produce some bogus message, the recipient will understand, but whatever it is, that is the key idea. So, once you have those threats, so in security community the key idea is always threat model, what are you trying to protect, and as I go along talk about security assertion, you will see those assertions only good for those scenario. If your application domain has other scenarios, then you have to deal with them. So, authentication you kind of know whether the key, whether the credit card, that 3-digit number, or whether multi-factor authentication, this is how I kind of do it. So, let us have a quick quiz so that I kind of understand, you know. So, the biometric, how would an attacker fake a biometric? How an attacker can fake a biometric? I saw there are so many biometric stations in this building, how would I fake it? Sorry, say again? Taking the fingerprint, right. So, I mean of course, I can chop somebody's finger and carry it with myself, or I can invite you for a tea or coffee, and then from that glass I take it out, put it on a thin film and put it on my finger. So, there are so many mechanisms and everything can be faked in biometric domain, and it is a big domain. So, that is the authentication. For encryption, takes care of the privacy issue. Any data I am communicating, you encrypt it, and then the encrypted message is not visible, and there is a huge market for it, of course, everywhere it is used. And the key idea is, assumption is this is secure or trustworthy, the sender area of the sender's computer, this is trustworthy or secure. Only thing is potentially unsecure is something may happen, that is while in communication, that is the assumption. Eventually, as we go along through these 2 weeks, you will see we will break all these, we will assume this is also not trustworthy, on Sunday we will break that also, or this is also not trustworthy, or the communication inside this also not trustworthy, then what, right. So, basically you encrypt any message, this is known as plain text, any plain text, let us say you are sending an email, that your computer will encrypt it, then send it out, encrypted message, and the recipient's computer will decrypt it, then you can again get the plain text. This is cipher text or encrypted text, right. And the way typically it works, you apply a key, you give the plain text a specific key, and you get the cipher text, and give the cipher text and give a key, you get the plain text back, it is just the inverse function. There are many kind of cryptographic systems, and symmetric crypto systems will have same key, both will have same key, asymmetric crypto systems will have different key, and key management is a big issue. Now, I am sending you a email and I want to encrypt it in a, let us say in a symmetric crypto system, this is easier because both have same key. How would I provide that key to you? Remember, I do not trust the communication link, how would I send that information to you if the communication link I do not trust anyway? Yes, please.
There should be an alternate
mechanism. I might walk to your house once and give the key or whatever it is. So, either way, key management, key storage, those are important problems too, which I am not going to talk about. Obfuscation. So, Dr. Karfa has a day dedicated for it, but I just want to touch upon the key idea of obfuscation is, if you have a design and you do not want your competitor to kind of get a clue of it or steal it, you want to confuse, put some more sentences. If you have a finite state machine, add bunch of random states and transition, do something to confuse the people. That is one way. You can also do logic locking, you can lock until somebody apply a key, they will not understand, or it will compute some wrong set of transitions, right. So, there are many ways of obfuscating, and again there is a day. Watermarking, basically you are trying to say this is mine, not yours, right, that is the kind of thing. And let me use, so in the pictures also earlier people used to sign, when people figured out sign can be faked, then they put some extra bunch of zeros and ones or some pixel RGB values on top of a picture, so that human eye cannot differentiate it, but if there is any debate any time whether this image is your copyright or my copyright, we will be able to establish it. And the Apple founder Steve Jobs took it to the new level, and most of you probably do not know this Franklin computer. This is when in early days of 1980s, there is a company called Franklin Computer. They basically took Apple II and called it Franklin S, and it is kind of carbon copy, not even you copy and rewrite yourself. And Steve Jobs was really pissed off. Those of you know Steve Jobs, read his biography, he basically used to work hard himself, push everybody else, to the extent people kicked him out from his own company, right. So, he does not have time, or he does not want other people to go to the court, defend and all that. For the first time it costed them a lot of money and 6 months to 1 year. Next time it was, I think it was settled in a week. he or his lawyer on his behalf basically told the judge, please press that button on the Franklin S, and the judge pressed the button, and this is exactly came up, stolen from Apple. This was programmed in the firmware. And the good thing about copier, the people who copy or cheat, they actually just do carbon copy, always that is the case, because they do not know what to modify. If they modify, they have to debug, and they do not have that much of money, IQ, whatever to debug, so they just take everything. So, everything was copied, including this footprint or watermark. So, if you press specific combination of button, it would display on the screen, stolen from Apple. So, I think that is a very interesting idea of watermark. The attacker will not know about the watermark. When you want to prove it anywhere, it is trivial for you. Any question? So, then last component is physically unclonable function. So, this idea actually, this is one of the interesting idea. When life throws lemon at you, what do? You make lemonade. If somebody throws you to the river from the bridge, what do? Just swim, right? Okay. So, when you do not have a choice of throwing somebody else back, you just basically swim. So, physically unclonable function, the inventor Srinivas Devdas observed something interesting, and that to solve a very interesting problem. Remember, I talked about key management is a serious problem. One is sharing the key, how do I share the key? Second is where do I keep the key in my device? It is typically in a non-volatile memory, supposed to be safe place, but all the side channel attack Dr. Karfa talked about, this whole key idea is either you steal it where it is stored, or when it is transit steal it, right, that is the whole idea. So, that is one problem, and this physically unclonable function solves another problem. Let us say somebody bought the phone and there is a problem, and everybody would be finger pointing, you know, right, when there something goes wrong, everybody wants to find a scapegoat except themselves. So, the idea is when say, oh, here is a chip and it was manufactured at TSMC Taiwan, they will say it was not manufactured in our facility, everybody will be throwing finger. So, that is why there is a mechanism, who is chip, who was in manufactured where, how many copies of that Amazon has. So, this keeping this inventory costs companies billions, and then everything gets screwed up. Instead, this physically unclonable function idea, let me talk about the idea for a moment. It comes from the thought of process variation. Let me show that to you. So, what you see is not what you get, this is what you see, this is what you want to get. Now, what is it? It is not important. Is it a transistor? Is it a connectivity? In a photolithography, this is exactly what you want to manufacture. Now, what would actually happen is the following. This will happen, and first of all, it does not look same. Second of all, the curves are not exact vertical. Third of all, some area is little thicker. It is all nanometer level. So, you have to understand that some areas are really thicker, some are thinner, some might not even be drawn. And what does that causes problem in layman terms? If you have an AND gate, it may not behave like an AND gate. You give 1 1, it may not be 1, it could be something else. And even worse, sometimes it will produce 1, sometimes it will produce 0. That is one problem. Second problem is the propagation time, the propagation delay, that differs from AND gate to AND gate. If you manufactured 1 million AND gate, each of them has their own personality. Some of them take 0.1 nanosecond, some 0.11, some this way, that way. Variation is minor, but it still there is a variation. That is process variation, and most designers, VLSI designers, struggles with this process variation. As it getting from micron regime to nanometer regime, smaller and smaller, this process is becoming bigger and bigger problem. So, Srinivas Devdas looked at it and say, oh, this is an opportunity. If everybody has their personality, if I ask 3 AND gate, 4 AND gate, ask them some question, how thick you are, how much of your delay, and if I create a signature out of it, that would be a unique signature for each chip. Then I can always trace back and say where it is manufactured, who asked it to be manufactured. It is not just that processors, 1 million processor manufactured the day, each of those 1 million can be tracked. When it was manufactured, at what time, where it traveled. So, that unique signature you can create, and that unique signature also can be used as a key. So, that is basically, I am not going to get into the detail how it is actually used as a key. as a challenge response pair, but that is basically physically unclonable function. Any questions are designed for security solutions. There are many such solutions. The key idea is you want to design such that it is secure by design, but as you will realize that people it would still be an attack. So, 2014-15 time frame, when I was trying to push this idea that security verification, which I am going to start now, there is a lot of pushback. What is there to verify? I am sending an email to you, it is encrypted, problem solved. I had to convince people that even if in your company somebody is designing the processor, somebody designing the memory, another group is integrating the processor and memory, do they test before giving it to customer, or you kind of believe each of the group, you do not. So, for functionality, if you want to verify, why do not you have to verify for the security? But now nobody asks that question anymore. People ask the question, can you do everything using large language model, and that is where the trend is going. People want to do everything using large language model, right. So, what I am going to talk about different types of vulnerability and how do we use security assertions and where does it fit in the big picture. Remember, we talked about simulation based verification and formal verification. Security based thing fits into the simulation based validation, because you are doing assertions, and I am going to do assertion for 4 different scenarios. So, before I go into this detail, let me talk little bit about assertions. So, first of all, in terms of verification effort over the years, the assertion based validation, what kind of people are doing, and this is kind of a number from that study, which is 32% or which is even less than 50%. If you look at how people were verifying your design, these were categorized for, this is for ASIC designs. So, assertions are used, what percentage of designs were using assertion based validation different year. So, for example, 2020 about 80%, not 80, about 75% of the design were using assertion based validation, and if you look at FPGA based design, then about 48% of them are using assertion based validation. Now, people are also using other things, as all of them are simulation based validation, code coverage, functional coverage, test generation based coverage. There are many categories, many information. I wanted to just give you a broader picture that no matter whether ASIC based design, FPGA based design, assertions are widely used. Now, let us talk about what is assertion, why do we care. How many of you used assertions? Okay. Assertions are there supported by every language in the world, every language. So, to understand that, let me take this silly example. You are opening a file results.txt to do something, and then you want to write to that file. If for any reason the file pointer is null, then you try to do this f write, it is going to produce segmentation fault code dumped. Can anybody tell me why would file pointer be null? I am just opening a file. Why it would return a null pointer, a file open function? It is a programming question. Go ahead. File does not exist. If file does not exist, it will create a file. That is the file open's job. In that directory, it will try to create the file if it is the first time. So, that will not be a segmentation fault. What else would be a segment? Sorry, second? Not sudo. Why do you need a sudo access? You are just running a program in user mode. I am sure you have used it hundreds of times opening a file. Memory run out, you may not have enough space, that may happen, but you did not pay attention. There is a W, I want to open in a write mode. The directory may not have write permission. So, it will not be able to open that file, it would be null, and you try to access anything from a null pointer, it is going to be a segmentation fault. So, typically a good programming practice is to anytime you open a file or do stuff like that, you check if file pointer is null, then you just print file can't open or whatever and exit 0, you just exit right there. You do not let it do segmentation fault. If segmentation fault happened, then you have to debug and all that stuff and find, waste time. That is exactly what assertion do. You assert file pointer. Now, in this example I have only one variable, this could be a complex equation, any complex equation you can put it there, assertion will monitor it. And from now on whatever security vulnerability I am going to talk about, once we understand the vulnerability, if I can express it as a equation, I just put it there. Of course, we still have to figure out where do I put it. Do I put it here, here, there, there. So, you have to find out what equation to put and where do I put it. Let us make sure all of you are with me. So, rest of the discussion today is all going to be about, I talk about a vulnerability and you tell me the equation and then you tell me where do I put it in the design. Any questions? Right. So, we talked about in a software program and the assert, and again it is going to be assertion failure, and even in hardware program thing same thing, it is a Verilog code, you can have assert property. Hardware has two types of assertion, immediate and concurrent. So, this is a concurrent assertion that is going to run in parallel. Immediate is inside if statement, if you put it wherever you put it, that is where you activate. In case of software it is always immediate, wherever you put it in a sequential execution, that is where it will run. So, in terms of applicability in a hardware design, people can do in gate level, RTL, TLM, you can put assertion wherever you want. Even in fact, assertion I am going to talk about simulation, but even formal techniques also use assertions, security assertions, and I will show those two. And then you can use for pre-silicon, post-silicon, after deployment you can apply anywhere, and I will talk about those scenario. Now, I am going to ask you a question. We talked about test, we talked about property, we talked about assertion. Can anybody tell me from these English words, are they related, not related, how are they related? I want to see hands please. Test, property and assertion. Yes please.
It's related.
How are they related?
Like in assertion we debug, so your testing is same. Testing
They are same. So, property P, assertion A, test T. Property equal to assertion, they are pretty much just the same. The way we distinguish, property is something in a formal or some description, assertion is something we embed in the design, Verilog, C, Java, wherever we call them, but they are actually same, they have same intent. How they are used, that is different. For property checking, when you property check, you formally verify, guarantee it. Assertion when you check, it is only during simulation. If that if statement gets activated, only then assertion would be checked. It does not guarantee you anything, but it has the same power. So, that is why I said they are equal. How they are used, it is different. Property is typically used in formal verification to provide the guarantee for eternity. Assertion is like a simulation time checker. If you run let us say 10 test cases, it might not activate it, but that does not mean your design is correct. That does not mean that assertion will never violate. Only thing it says about the time you simulated, that assertion did not fail, but if you simulate another millions of test cases or millions of clock cycle, maybe it will violate. So, that is a no guarantee. It is actually people use that as a runtime checker, and this is a static time checker. You can think of it, this is a dynamic verification, this is, but their power is exactly same, what they can represent exactly same. Now that we established it, property, now you think of an assertion or a property, every instance of it, let us use the word assertion, because in the simulation context it makes sense. Every instance of it, every point is a test. So, I can have millions, actually infinite number of tests on this line. If property or assertion has been checked or guaranteed, you proved something for eternity, but if you checked a test, you only proved for that instant. So, then if you want to put that logic of how I did, T is a subset very tiny subset of a property. If you can have infinite of them, then they will be equal to the property. because a property actually checks one point in the story. Different test case will check one instance of that property in that time frame. Yes, please.
Sir, can't we say that property is the verified assertion?
We can say the opposite way also. Assertion is, so sometimes in the community people use property to mean it is a behavior. What is your expected behavior, people call it is a property. So different use different terms, but they actually mean the same thing, right. The way people use now property, they use for verification, formal verification people use the term property, the simulation based validation people use the term assertion, but they have equal power. So the way property or assertion and test have no equal power, test has only one instance in the time story. Yes, please.
If we take a test suite that includes all the testing, then can we say test suite is equivalent to assertion that tests all the?
Can you use the thing, please? Go ahead.
Sir, when we talking about testing, we test suite includes all the tests that are possible on a system or some module.
We never do that. So the reason is it is not possible to try all possible inputs. If that was possible, then we do not need formal verification. As we showed in the add example, the number of possible inputs you have to try even for a adder, that is practically infeasible. So now we kind of go forward. Now let us look into the assertion based validation methodology. How is it used today for security? So basically from whatever design is it, you do some vulnerability analysis implicitly, explicitly, automatically, manually, all of that can be discussed, but you need to know what are the vulnerabilities. For each vulnerability you have to have assertion. Again I said generation, it could be manual, automatic, we will zoom into that, and then you get those assertions, then you put those assertions in the design, and but once you put the assertion, you also need to talk about how do we activate those assertions, right. That we will talk about. Then you need to generate test and activate those assertions to kind of check they actually work, right. So let us first talk about assertions are for covering certain scenarios. Again this could be functional scenarios. In this case I am just focusing on security vulnerability. So that is why I am talking about it, but this could be functional scenarios and you get the assertion. Once you have the assertion, why do you need test? Because I thought we discussed assertion is more powerful than test. Why do I need the test in the story? Why do I need even this block? Why can't we get rid of all of it? Let us answer that question. Why do I need it? What is the job of it? I do the analysis, I find the vulnerability, and I just put the assertions in the design, so that during runtime if anything goes wrong, assertion will fail. I know. Why do I need the test?
Sir, because after we do the assertion, we need to test. We need the test cases so that we can test that assertion.
We want to check. Thank you. That is correct. We want to check if the assertion is valid. Remember, assertion we wrote assertion within bracket file pointer, but assertion could be very complex equation also. The equation you wrote to represent that scenario, complex scenario, maybe you forgot it, A greater than B and C, maybe it should not be greater than, maybe it should be less than or greater than equal to. So therefore you need to know, because you just put something in there and you expect if there is anything wrong somebody will tell you, but you never test it. Simple analogy, let us say you hired a bodyguard, right. If you hired a bodyguard, assumption is if anybody attacks on you, bodyguard will protect you. So in this example you is the design, bodyguard is the assertion. Now the question is, how do you know when you are in your life is in danger, your bodyguard will help you? How do you know? How do you test it? So that is the idea why testing is needed. How do you test it if bodyguard will work?
Simulate.
Sorry.
Simulate a scenario.
How do I simulate a scenario?
Fake intrusion can be, and we see what the.
What is the test? Tell me what is the test here, because I am trying to get to why this is needed.
Test is, sir, that somebody like a thief or terrorist or somebody can try to simulate that attack on me, and we can see.
So you hire an attacker, You hire an attacker who will attack you, but bodyguard should not know that you hired that person. Bodyguard will try to defend you, then you know how it worked. So, you not only have to pay for the bodyguard, you have to pay for the attacker. If you do not do that, then you actually do not know when your life is in danger how your bodyguard will react, right. Same analogy here. You put all these assertions to check whenever vulnerability happen, it would stop and report, and you do not know that will happen unless you generate test and try to activate them or create a scenario. So, if you understood that, tell me in the file pointer example what would be the test? The file pointer example, let me try going. So, this one, this assert f, if I put an assert f, whether it should be f or it should be not f or something else, how would I test this asserts this statement? What would be the test for this scenario, for this assertion statement? Now, tell me exact thing that I can do. I am running that program in a directory. What exactly should I do to create a test case that would activate this assertion? I want this assertion to fail. What should I do? Yes, please.
I should try to open a file that had a read only attribute.
Yeah. So, I create a file in that directory, take the write permission off, something like change mode minus w results.tex. So, first I open that file or create that file, then I take the write permission off, that is the test case. Then you run this program, then it would fail. It is supposed to fail if you wrote it right. Maybe then you will say, oh no, I need to put a not here or some stuff like that you might have to do. So, I want you to understand a test case is something practically you can do, and in this particular case as we go along we will talk about test case and test generation, right. Now, let me show you the big story how actually work. First of all, you need to know what your threats are, a threat model is, what you are trying to cover. If your threat model is not correct, then anything you generate is not useful. So, what your threats are, then you do, given a design, you do vulnerability analysis. This is your design that is coming in, you know what you want to check for, you check those and you generate the assertion, and I will show how to do and what to do. I will zoom in further, and those assertion you put it into the design and you do assertion based validation and all that stuff, you basically simulate whatever you do, and if there is a failure, then basically you fix that in the design. If the assertion itself is invalid, remember two things can happen, either design has a problem or something is going wrong, or the assertion you wrote A and B or A greater than B, that itself is wrong. So, it could be you are fixing the assertion or you are fixing the design, and that story continues. And because it is simulation based validation, there is no guarantee how many assertions are needed. Same thing for formal verification. Property checking guarantees you design satisfies that property, but how many properties should I verify to completely verify the result, that is an undecidable problem in computer science. Analogy, traffic light controller, we check both sides should not be green at the same time. If you check that property, it only guarantees that thing will never happen, both sides should not be green at the it will not guarantee you, maybe both sides would be red all the time or one side will never become green. All of those things can happen, and that is not a correct design, right. Whichever property you check, it guarantees for that, but how many properties do I need to do? Do I have enough properties? Do I have less? That is a undecidable problem. Now, how does this assertion generation happens? The way it works, basically I will zoom into some of them. It could be static code analysis. So, their software, a program will run through the code and figure out are there vulnerabilities, right. Or it could be when things are running, it could be doing execution trace analysis like malicious implant. There is a day dedicated for hardware trojan, you will understand. It will do that kind of analysis to find or create assertion and put it onto the system just to check if there is a Trojan, if it gets activated, that assertion will fail. While you are running, program execution will fail, it would report something, so that you can go back, debug and fix it. And the assumption is you were not able to find that Trojan before execution. If you could have found it, you could have got rid of it, you do not need that assertion to run. In fact, in real world scenario, many companies, they check everything before it goes to the customer, but they still keep some assertions in the system, the very critical one. The reason is, some of the scenario you checked, maybe you could not check it completely, or even if you checked, maybe the surrounding conditions will change in such a way that you did not envision as a requirement or a threat model. In your threat model, that was not there, how attacker will try to attack. I will give you an analogy. So, most country, when they design their defense equipment, they do not want, they want to keep feature in it, so that any enemy hand, when it goes, enemy will not be able to figure out, typically in the form of kill switch. If it figures out or thinks I am in enemy hand, it would self destruct. And there was a war, I do not want to take the country's name, one of the country won the war by using the kill switch on the other country, because the other country, whatever purchasing they did, they embedded kill switch that could be controlled by the other country. They all had to do just enable the kill switch. So, the system was legitimately thinking I am in enemy hand, I need to self destruct, they just self destructed themselves, war was won. That is one feature. Another way to think about it, many embedded devices, a common feature is it should be reactive. What does reactive mean? If the, remember the Mars Pathfinder, it was supposed to walk, if it falls down on the head, there has to be a mechanism so that it get up and keep moving. Most robots are designed that way. If it falls on the side, it should not be just lie there, they will try to get up, that is the reactive. If it gets into some water, it will try to react. If there is a fire happening, they will try to react certain way. To you or me, it may seem like, well, that makes sense, but from a security perspective, it is a bad idea. Let us go back to the defense equipment again. If the defense equipment goes to the enemy land, now enemy can open it up, but it would be a destructive behavior. If they open it up, before they figure out what is happening, they will not be able to run it and figure out most of it. Instead, they might start little fire next to it and see what the equipment does. They throw some water at it, see what the equipment does. They kick it and see what it does. You are basically reverse engineering the functionality and capability of the enemy device. So, the feature or functionality that seemed like very natural, being reactive to the environment, now I can use it against you to figure out what are your capabilities. So, the country that found the opponent country's equipment would be able to figure it out. So, no matter how you go, you self destruct, that is also a problem. You have reactive capability, because if equipment lands in a place, there is a lot of sand, or you thought there is a sand, but it turned out to be some gooey surface, how would it react? So, even that can be hacked. So, similar, that is why the analysis and correct model, threat model is important. As I said, in software there is only immediate assertion. Wherever you believe problem will happen, you insert an assertion like file pointer null. In fact, those of you worked or plan to work any ACI level software engineering institutes 4 or 5 level company, the companies that produce reliable software for safety critical system, writing assertions is a requirement. For every line of code you write, you have to write 5 lines of comment and 1 assertion, you have to write. Of course, there are more requirements, the variable naming convention, then you have to do code work through every week with your colleagues, and there is a lot of requirements to develop safety critical software, but assertion, writing assertion is one of the requirement. So, in a software program you write exactly when you write something, then you write the assertion. Now, even some assertion may look silly. For example, you wrote C equal to A plus B, if you are doing code walkthrough, next one would be assert C and C not equal to A plus B, something like that, very easily. Now, you might say, wait a minute, if this has to work correctly, this has to work correctly, what would go wrong between? Now, there are many reasons people do that, but you want to check the value of addition happens to be correct with that one. It may not be as silly as this, most of the time it is not this silly, but some people even write that way. You do addition, then you check is the result matches with the expected result, right. So, immediate assertion is you put exactly where you have a statement. For example, if you have a if and you are doing some computation and you need an assert right there, you put right there. This is known as immediate assertion. So, like user is admin, request to an acknowledgement. Concurrent assertion is assertion something that runs in parallel. It does not matter where you put it, you do not put inside if statement. So, in like Verilog example, always is a parallel statement. So, if you have always, you have many always blocks, this concurrent assertion will sit in parallel to those always blocks. So, always blocks are running all the time in parallel, and this, think of this also an always block, think of it. This is another always block that runs all the time in parallel. That is the idea of concurrent assertion, and I will show many examples of concurrent assertion. Any of you have any confusion of immediate and concurrent? If it seems like they seem same to you, then I can draw another picture. Any question? So, if this is your program, think of processor, memory, you might have written this way, but they are in hardware they are running in parallel, in software they are sequential. So, if they are running in parallel, if you put something inside, that is an immediate assertion wherever you write it. But if you want to write a concurrent assertion, you have to write it here. This is a concurrent assertion in your program. So, this is an always block, this is running in parallel, this is also running in parallel, and you can put as many concurrent assertion as you want. That would constantly monitor anything goes on here, here, they are all running in parallel, all the components. So, here is a example of a mutual exclusion story. Think of a traffic light controller, both sides should not be green. Think of this request, one car is waiting is one of the street, this is a second request, another car is waiting, and think of this grant or acknowledgement is this side green and this could be this side green, but we know that should not happen. This analogy can apply to anywhere else. Let us say there is one book in the library, multiple people requesting, but only one of them would be true, or there is a one printer, multiple people trying to print at the same time, only one would print. So, anytime there is a resource constraint, you have this notion of request and acknowledgement, right. In this particular scenario, let us say I said both should not be true at the same time, both of these grant 1 or grant 2, the way you write that assertion, you basically say grant 1 and grant 2 should not be true at the same time, that is your assertion. And I keep talking about the complex expression, that is your complex expression. Any vulnerability you want to model, you find what that like equation, put it inside the assert statement. This will guarantee you, because remember this one is easy to view and analyze, this could be a really million line code, and this request come at the beginning of million lines of code, this comes at the end, you just put that in, anytime it violates, program will stop right there, and you know it will tell you which line it failed, which program, your debugging time got saved there. Same thing analogy can happen for fault injection attack. How many of you know what is fault injection attack? So, this is a doorknob, remember I told you I can hack anything with the right equipment. Fault injection attack, anybody's door, most US doors are smart door. So, where you punch in thing, and many cars also have this punch pad. So, you punch in your code and you get in. Of course, if you can know somebody else's code, that is easier, but if you want to do fault injection attack on it, right. So, then you have to realize that the way this doorknob works is basically some form of state machine. where the device is constantly waiting for somebody to punch something, it is waiting that state, and if somebody enters a wrong key, then it comes back again, wrong password comes back again. If somebody enters a correct password, then it will allow access and open the door, right. And the numbers I am writing at the bottom of everything, this is called state encoding. So, then if I can just, and if you look carefully, this number, if it is not visible from the back, this number is 000 and allow access is 100, Hamming distance of 1. Today's laser pointers basically, so there is an integrated circuit of course inside, and if I can throw a laser beam at it, if I do it right, hit it right place, I can flip this bit from 0 to 1. So, I am at this state, I did not enter password, I can flip that bit to 1. So, it will become this state 100, and I can rotate the knob, now I can get in. So, today's laser fault injection attack or the laser beam is smart enough to flip any one bit for sure, any one bit. Up to 2 bits can be done by pros like me, beyond 2 bits 2 consecutive bits, if it is far away no problem. More than 2 bits is not state of the art, people can do with some probability, it is not like 99% guarantee, right, it may or may not happen, but 1 bit is like a piece of cake. Now, some of you are looking at it thinking wait a minute, I am just trying to fool you guys, this state is here in the state machine, that state is there, why flipping something here will take you there. How many of you are thinking like that? Yeah, you are thinking that way because you might not have done digital design or the way it is implemented. The way it is implemented or any state machine, the way it get implemented, there is a state register and then there is a combinational, a sequential logic, state register and a combinational logic. Depending on the value here, it does the action. So, the way you are visualizing here as if there are 4 different registers, no, there is only one register, because a system is not in all the 4 states at the same time, it is only in one of the state. Which state? That depends on the value on that register. Initially is 000, all I have to do through laser beam, I have to change that first 0 to 1. If I do that, this logic will believe I have entered the password, that is how it became 100, because typically this logic updates based on what is going on. Because it observes it's 100, it will open the door for me, that is the catch. But again it is difficult, it is not for naive people. First we need to know the state encoding or FSM, what is implemented inside, we need to know. Second, we need to know in that chip where exactly is that register. Third thing, we need to know what is the Hamming distance between wait state and the allow access state, which bit need to be flipped. Out of these millions of possible point on this chip surface, where exactly that bit is, you have to exactly point to that one, otherwise it will flip something else, some random stuff will happen. Yes please, I saw a hand. Okay, thank you. So, okay, that is laser fault injection attack. The way we talked about power side channel attack, there are different types of attack, this attack is very powerful, and the way you fix this, the way you design finite state machine. If I know the capability of a laser beam is to flip 1 bit, then I want to make sure between non-secure or normal state and secure state, the difference is more than 1 bit. You have to do the state encoding. So, in this example 3 bit register will not work, you need 4 bit register, you need to make sure the number of Hamming distance or the difference of number of ones. So, if this is 000, I could have created this maybe 1100, at least 2 bit difference, assuming laser beam has the capability of flipping 1 bit. If laser beam has capability of flipping more than 1 bit, I might have to do 1101. Of course, I have to make sure other people have encoding. So, we have to make sure the Hamming distance difference between these 2 states and these 2 states is more than the capability of laser beam, how many bits it can flip confidently. Now, laser beam is done, I talked about this one. How do I put an assertion here? That is really my question now. All this discussion is great and wonderful. At the end of the day, you as a security engineer in the company, you have to write an assertion, put it somewhere. What do I write? Same thing I tried to simplify, get password, check password, and I simplified, instead of 4 state, I simplified 3 state. It has other problems, I will come back to that later when I talk about Trojan. Right now, let us focus on those 3 states. You as a verification engineer, what would you test? Yes.
So that the sequence is there. If check password state does not occur, then the operation state should not be allowed.
Right. The problem with that philosophy, that is what everybody does. You know what states are there, you know what are the valid transition, everybody checks for the valid transition. People do not check for unspecified transition, unspecified state. The problem with that, if you have n nodes in an FSM, you have order of n square transition. Let us agree with that first. If you have n nodes, there are order of n square transitions possible, but in real design you are going to have order of n states. Like here you have 3, if you ignore some of them, 9 was supposed to be there, but if you ignore few of them, there are about 3 or 4 transitions. That is what people are going to test. People are not going to test the other possible transitions. If through Trojan, laser fault injection, if people create other transition, nobody is testing those. So, if you want to test those, let us say you have an typical FSMs are really large, 50 to 100 nodes, 100 square, that is a lot. Testing all of that is going to be eventually impossible. But I will show you a simple assertion, you will feel like, oh my God, it is so silly, how did not I think about it. So, here is the assertion. The assertion says, no matter whether it rains or shines, from G there should not be a path to O. If any time during simulation somebody is in G and happen to reach in O, how it reached I do not care, I am going to stop there. I am going to break the simulation, exit it right then and there. I will not allow that person to get to that operation and allow to get in, I will just alert, open a red signal and keep beeping, right. So, that is basically the key idea. Any questions on this? So, I do not need a n square assertion, you could have achieved it using n square assertion for every possible path that was not allowed. Remember n square, order of n square transitions possible, out of the order of n are legal transitions. So, it is really the order of n square minus order of n, that are still order of n square. Those transitions that are not allowed, I want to write an assertion for each of them. I could have done that, or I could just write smartly one of them. If this is the only transition should not be allowed, no matter how, whether it come through this, come through that, goes through this, I do not care. If somebody is there, should not be able to reach there. You can write it many other ways. Then the last example I will take before we close for the day is, remember we talked about any design have 2 mode, normal execution and manufacturing testing time execution, right. In manufacturing testing time, so early days, not now, before 2000 attackers used to quickly change for normal execution mode to test mode, and they used to dump everything from the scan chain. Those are not possible. So, if you want to put an assertion, you are saying if you are in normal mode, which is not JTAG mode, JTAG is basically the port, not JTAG mode, then JTAG output should always be 0. If you are doing normal execution, you should not be able to dump anything, nobody should be dumping anything, it should be all zeros all the time. And if it's somebody is dumping, at some point that would be non-zero values, then it is going to stop and break. So, I am going to stop right here, and in the next lecture we are going to talk about different type of assertion based validation. Thank you.
this case. Which one? 2 plus 3 equal to 5?
না 10 না ওই 9 পড়ে আছি গো আর পড়া
You can start.
Good afternoon. In the last lecture, we talked about security assertions and how do we generate our security assertions. Now, I am going to talk about how do we apply those security assertions in specific scenarios, and I just decided to choose 4 scenarios just to show how do we apply those security assertions. Now, where does these scenarios come from? If you are a security verification engineer, scenarios comes from your threat model. What are the threats you are thinking? If it is a system on chip, then what are the things you are worried about? And this list comes from, if you recall, common weakness enumeration, common vulnerabilities enumeration. So, that database, these are the typical vulnerabilities, and the list of 4 I am showing, it is one of those 4 out of these 7. And if you recall, some of the vulnerabilities may not be unique, it may be a combination of the vulnerabilities. For example, an attacker might be able to try information leakage using malicious implants. So, for example, if you think of this circuitry, there is a hardware Trojan and this is the trigger corresponding to it, and the job of the trigger is basically to make sure some assets, this could be the key, birth date or anything that you do not want it to propagate to a primary output or an observable point, you do not want it to operate, and there might be if statement that stops it. That if statement might be saying if you are a privileged user, then something is supposed to propagate. In a normal execution mode, the privileged user is supposed to be 0, that variable, but what Trojan does, whenever you as an attacker want it, it will make that one 1, although you are in user mode, but that variable would be flipped to 1. It could be done through Trojan, or as you have seen when I talked about laser fault injection attack, it could be done through that, but no matter what it is, 2 attacks collectively will allow this information to leak from the point of assets to the payload. Now, for malicious implants, we have a day dedicated for it, but if you recall, the threat model for the malicious implant is the attacker is going to hide it in a place that is difficult to detect. For example, instead of putting on the top of the table, maybe it is going to put on the bottom where the visibility is less, people are less likely to bend and look. So, then if that is my threat model, then rare variables or rare signals is what we should be looking for. For example, in this definition, if we say a particular variable signal S becomes 0 with 99% of the time and it becomes 1 only 1% of the time, then that signal is rare for value 1. So, therefore, if we analyze the design and find, let us say in a design we have 3 rare signal A, B and C out of millions of signal. Depending on how many signal rare, what is your threshold, what is this cutoff, is it 1%, 0.1%, 5%. Once you change the threshold, number of variable will become rare, that set will increase. Once we have that set, now the assertion, even if you write manually, assertion would be, there are different types of assertions possible, because you do not know whether each attacker is going to create a trigger of only one signal, 2 signal, 3 signal. So, then you have to consider all possible combinations. So, if I have 3 rare signal, so here are the 3 assertions. If I consider a combination A B B C C A, here are the 3 possible combinations. If I consider all of them A B and C, here is the combination. Clearly, unless you put a really high threshold number of signals too much, it is going to be exponential number of assertion. So, there is another level of elimination you have to do, but nonetheless what I wanted to demonstrate to you, the automated system that generates it, this is the principle or philosophy it applies to it. What is the threat model, and based on the threat model, what are the possible assertions, and generating those assertions. Now, of course, there are many techniques, I will talk 1 or 2 of them. How do we reduce the set, yet you get some level of guarantee? You are willing to sacrifice your exponential list, exponential in terms of number of rare signal, and yet you want to maintain certain level of vulnerability coverage. The way we talk about functional coverage, here we talk about vulnerability coverage. Any questions on how do we apply security assertions, or how do you generate?
One question was there, like this is a rare signal, so we have put an assertion based on rare signals, but what if the rare signal is genuine? It's rare, but it is there.
Interesting question. So, the question is, we are assuming the attacker is going to hide or create a trigger consisting of rare signal. Therefore, if that combination is true, then we are basically trying to make the assertion fail and stopping the program. So, the question is, what if the exact thing we are thinking that A and B or not A and B, that scenario or that gate AND gate is actually part of the original logic functionality. What do we do about it? So, the thing is, that story is going to happen. Even rare signals are still the signals in the design, and even if it is 1%, it is still going to happen at some point in time. With low probability, even if you simulate, the chances of it happening or failing is low, and bigger the trigger is, chances of that happening, unless you are running millions and millions and millions of test cases and billions of clock cycle, even if it is part of the original functionality, it will not even happen. Only time it will happen if the attacker is trying to change the input, because what is attacker's objective? Whenever it wants to mount the attack, it will give the primary input in such a way, so that this trigger condition becomes true. So, that way we are kind of, it is true, it is going to be a lot of false negatives, but the thing is, the odds of that happening in normal execution is low, but would such gates exist in normal logic? Yes. So, now let us look at illegal states and transition. So, some of this we talked about in the context of laser fault injection attack in the morning, and the idea is, when you have a lot of states, they may be connected, some of them may not be connected, like some of the unspecified state. Where does this come from? Let us say you wrote a if then else statement or a case statement, where you talked about 3 scenarios. In your mind, you are thinking the finite state machine will have 3 states, but in reality, if you synthesize using any synthesis tool, for example, Synopsys design compiler, whether it does one hot encoding or binary encoding, it is going to create 4 states. You did not design it, you may not pay attention, you may not test, but that state will be created. It will not look like this. Recall the register it will create with 2 bits. So, it has a probability of those 2 bits becoming corresponding to this variable 1 1 at some point, right. And some of these states you can designate as unauthorized state, authorized state, protected states. In layman terms, think about the password check we worked on the doorknob. Think of this one, somebody is trying to enter the password, this is checking the password, this is opening the door lock. So, then key idea is that we are trying to do that, we are trying to create assertion of So, we do not want such a transition to happen from an unauthorized state directly to the protected state, like door opening without going through the password check. We do not want that to happen, and that you can similarly we do not want anything unspecified functionality, although I have drawn this link, but technically speaking this should not have any transition to any of the states, but this is the most dangerous. From nowhere it should not be opening the door. And you can write a property as simple as by the state's name implies if you are in S1 you should never go to S3 no matter how it is. Although I show a transition like this in the diagram S1 to S3, it could have been via something or some other mechanism, but such a transition should not happen. Any questions on illegal states and transitions? Remember, when state machines are this simple, you might be able to write by hand, it is possible, but when you have a complex state machines, lot of parallel concurrent finite state machines running in parallel, doing analyzing manually, figuring it out is kind of impossible. That is where you kind of need automation and understand that basically whether it is a unauthorized state to protected state or unspecified state to protected state, all of those assertions need to be generated automatically. Now, in terms of information leakage, this is kind of involved, I will try to do as easy I can. So, tomorrow you guys are going to play colors, right. So, let us assume each of you decided to use only one color, one unique color, and your hand is full of that color. Now, whoever you apply the color, subsequently if we take any person at the end of the day, look at the number of colors in his or her body, then I will be able to figure out who are the people this person came in contact with. Now, this is not an unique idea, even in COVID days the contact tracing, that is how it worked. If you got COVID, the scary days of COVID, then where did you visit, then all of the people you visited or that vicinity, we kind of assume those people are also contact tracing individual, then we translating where did they go, it is the same analogy. And why are you talking about this analogy? Because I know there are certain variable like S or certain variable like S is a secure asset, think of a key in the program. I do not want that variable to mingle with other variable such that somebody observing the primary output get a smell of that variable, I do not want that from a security expertise point of view, but the way you written program, this variable would be used in different places, in the part of the if statement, on the right hand side of somebody, on the left hand side of somebody, and that is the mingling story, right. So, here you see the S is on the right hand side and left hand side is A, that means A is getting information from S. If S is a secure asset, now A suddenly become we call it contamination, it gets contaminated. If anybody get a smell of A or get the color of A, it gets the information about S, and this is a very trivial way of showing through if statement, for loop. There are many complicated relationship. Question is how do we know? The way it works, there are many other ways of figuring out. The information flow tracking mechanism basically says as many variables as you have, you create those many tag variable, like for S we created S underscore T, for B we created B underscore T. Anytime there is an assignment A equal to S, we create another assignment A underscore T equal to S underscore T, and this story continues for every assignment, for loop, if statement. There are ways of doing it, and then what you want to do, after we instrument with tags, we really want to check if B is the prime output variable, we want to check that S implies T, tag variable of S implies it is not tag variable of B. If their tag matches, their color matches, that means B, which is a primary output, anybody can see it, it will get information about S. That means there was a path. This basically means if this property ever fails, that means there was a path from S to B. if I draw it pictorially, let us say this is a design and S is somewhere and B is primary output, that means there is a complicated path, no matter mingling, eventually this value can propagate. That is the information leakage story. Now, in reality things are lot more complicated, many times we may not be able to do it, because remember this is through simulation, and simulation means there is no guarantee, because AST and all this stuff or this assertion failure will happen only if you activated all of the paths. This could be a if statement, this could be inside for loop, another if statement. The probability of each if could be very low, and if you multiply those probability of this path happening during simulation is extremely low. And if you did not run enough test cases, in reality there is a leaky path, but this did not fail, falsely you will assume, well, this design do not have any leakage problem, but that is not true. So, that is why if there are formal guarantees that this property itself or assertion itself, you can call it as a property and you can do model check on it. Exactly this one, you can do model checking on this property, that in the eternity of this design execution, S underscore T will never imply, always it would imply, such as always S underscore T implies not B underscore T. You can check all of that stuff. In this domain people also do static analysis, but that is not under purview of this. The way they do static analysis, something like this: if AND gate has one of the input variable which is secure, the probability of this propagating here is 25%, because of 1 1 makes 1, all 0 0. So, you can compute the probability of this propagating to the output and you continue that at the gate level. In the RTL level or in the program level, if you have if statement, you compute those probabilities and compute how it flows. So, if you have 2 or 3 layer, probability is already very low, it may not seem much, then how is it useful? The way compiler gives you lots of warning or error, this tool will give you lot of list of leaky path with the probability number. Designer will go by the highest probability and slowly go one by one to figure out which one should I fix first, or do I fix, or is it is yeah, it is a reasonable path, there is nothing to fix about. So, again the key idea is I wanted to explain that information leakage is a serious problem. I explained a method of using tag, this is called information flow tracking. Using tag, how would you instrument the design, and if you do instrument, then you can put an property like this. So, then your assertion generation problem is not just generating assertion, you also have to instrument the design, otherwise assertion generation would be useless. Any questions? Permissions and privileges is actually similar, I am going to skip, I have used the same finite state machine. So, that basically we are just saying it is not that S2 cannot go to S3, it is basically it has to be also a super user or whatever it is. So, some of the properties kind of look similar, but it basically this property is, are you authorized to go to that state, it is not saying do not go to that state. Here are some results, but simply if you are working in this area and you want to do the security assertion, your objective is to what is the minimum number of assertions I can generate to give the full coverage, whatever your threat model talks about it. And of course, you have to consider how much of time it would take and memory requirement to kind of for you to run those assertions. So, before I kind of conclude this kind of discussion, one thing I want to talk about, there are also static analysis tool which would do this on your behalf. So, similar to the assertion generation I talked about, there are many tools. One of the early ones is Goldmine, then there is Harm, and there are many of them. They automatically analyze the design and it will generate assertions for you, right. That may not be the exact security assertions you are looking for, but that would create certain variables and generate. This is another static analysis tool it may not, just on the surface it may not look like these are security assertions, but if you look closely, buffer overflow is one of the common weaknesses. So, if you can get rid of buffer overflow issues from your design, then you are on a good area. Same thing about null pointer, valid pointer, memory allocation and all that arithmetic, undefined shift. You see the word undefined, that is kind of attacker's paradise, undefined, unspecified. So, there are tools that can do analyze your thing. So, this particular one is from trusted execution environment, security enclave, if you recall, security kernel, the mechanism that allows us to do HTTPS and all that comfortably. Even all their application specific interface, those API functions, if we just run the open source static analysis, this is called linting tools, you can see the basically there are so many violations. There are so many violations of all that kind. That does not mean actually that API is buggy, that only means that has so many vulnerabilities. Security enclaves which is supposed to give you protection, think of your bodyguard, the bodyguard's body itself needs medical attention. So much health issues with any of these function calls. So, to conclude the discussion of basically this issue is that simulation based validation, security validation is applicable for large design, but you cannot guarantee completeness. Formal methods gives mathematical proof, but you can apply only small and critical component, and assertion based validation is widely used for security verification for hardware, software as well as firmware design, all of them and actually together. So, what I am going to discuss now is basically how do we generate test to activate these assertions, as well as how do you refine some of these assertions. So, in the previous lecture we primarily talked about generation of assertions, but now we are going to talk about we will briefly touch upon that assertion generation just to recap, but we will primarily focus on how do we activate these security assertions, so that we know they are valid, and what is the scope or opportunity or challenges of doing dynamic refinement of those assertions. So, as we discussed earlier, all the security assertion story starts with the threat model. What are my vulnerabilities for which I have to generate the assertions, and there are a lot of automatic assertion generation method, such as some of the early ones or popular ones are Goldmine. I will briefly talk about their basic philosophy, and all of these you can download and run. They are very stable, although it is academic tools, but they are very stable. The basic philosophy is that you run it, you have a design, hardware, software, it really does not matter, you have a design, you basically simulate it. You simulate and run, you can run with random tests and there could be efficient tests, but you run, and whatever traces it produce, the tool tries to figure out are there any invariants. For example, when things are getting generated, let us say you are building a truth table A, B and all that, and it is observing, is it possible whenever A is 0, B is 0, is it possible when A is 1, B is 1 and so on and so forth. After observing, it is trying to figure out an invariant that A implies B, that whatever the value is A at specific clock cycle time, B also have the same behavior. It is trying to figure that out, instead of a designer saying it, instead of somebody analyzing the circuit figuring out, based on the simulation traces, it is trying to figure that out. Now, as you realize, maybe the up to the time it ran, that relationship exists. Now, this is a simple relationship I talked about, it could be really complicated relationship, big equation. Is it possible that if you run 10 minutes more, this relationship will fail? That is possible. That is why once these tools figure out this kind of invariant relationship, then they do model checking. and to check if that is that true for eternity, and then that becomes an assertion. So, this is the kind of story of generating functional assertions, and so, but these functional assertions are not kind of useful for monitoring security vulnerabilities. Can you tell me why? Because functional assertion checks for expected behaviors. Security vulnerabilities is exactly inverse of that, unexpected scenarios, exceptional scenarios that people typically do not specify. That is not completely true, because if you think about an addition, what will happen in an overflow, any architecture document clearly specifies that. So, in general I cannot make that statement, but most of the time people talk about what is the expected behavior of this design, and that is why it should not be surprised that for different design, if you kind of just use assertion. So, you insert some vulnerabilities, that is what we did. We inserted some vulnerabilities, we generated assertion using Goldmine, lots of them, and we ran them just to see how many of them are covered. So, there are two approaches. One approach is what I talked earlier, specifically for scenarios like permissions, privileges and so on and so forth. You generate assertion to monitor security vulnerabilities, versus you generate generic assertions, functional assertions, and you hope those vulnerabilities will be captured. And for certain small designs that might be the case, few designs as you go bigger and bigger, remember AES is not a big design at all, even for designs such as AES it will not be able to cover anything. Now, so this is the overall view I talked about. Just to summarize, once you know the threat model, you kind of do the vulnerability analysis, you generate assertion, and then that assertions you put it in your design and you verify, simulate and all that, and you have two scenarios at that point. Either the assertion failed, it is a problem with the design, you fix the design, or the assertion itself is a problem. So, for example, in the assertion, when you put inside A and B, maybe this expression you wrote it wrong, it should have been not A and B. The understanding itself was wrong while you were writing the expression. So, then that need to be fixed. We already talked about the sample examples of, I am going to skip all of that. So, the question is now that we have all these assertions, how do we activate them? How do we check those assertions are valid? How do you guarantee when actual problem will happen, this assertion will actually fire for right reasons, not for wrong reasons? So, to understand that, we need to understand that we are talking about test generation. So, what is a test generation problem? It is an algorithm, you can do it manually, that would produce something. In case of processor validation, you need to produce some assembly instruction that you can run on your design, and it is supposed to produce some result, and you can check with the expected result. In this context, most of the companies, what they do is some form of constrained random test. So, random would be random, as the name suggests, you keep on applying some inputs. Constrained random is you kind of know where you are, what you want to achieve. So, for example, you know, if you have lots of branches or if statement, you kind of say, well, I covered 80% of the branches, but the 20% of the branches that you did not cover, you can keep running more and more tests. So, this is basically number of tests, this is number of tests, and this is basically branch coverage. Let us say branch coverage is our criteria. But normally if the branches have rare condition, the condition itself is extremely rare, you can keep running, it is not going to go up too far. So, that is why what company do, whatever they can achieve by random, constant random, remaining they try to cover through various other mechanism. It may sound funny, they actually use some of the manufacturing tests also, just to increase the coverage. Then people would add some directed tests, some ATPG tests. Direct test people would write manually. If I know which branch I need to cover, they try to figure out what do I have to make the initial condition for this branch to be activated, right. So, if I want to do, so this, let us say this is the initial state, this is one of the branch that is not covered, and you keep on running a lot of tests, it may not activate, or you can just manually write one of the tests that would take you right there. Only problem is for small programs you can look at, okay, this is the if statement, I need to do a greater than 5, if I want to make a 6, what do I have to make to the previous assignment, what do I have to make to the for loop, you can keep going back and manually write. But when you have millions of instructions, this is not going to work, millions of lines of code, this is not going to work. So, then you can do you can kind of use kind of automated method and to generate, but the problem with the automated method is, remember the automated method whatever you are trying to do manually, it would still try to do the same, but while it is trying to do, if the if statement has a rare condition, then you have to make the rare condition true. For you to activate this assertion, it has to make the rare condition true, and it is just not the rare condition true, you also have to make p as true. Remember this p could be a complex expression, it may not be one variable, and you have to make p true and then q as false in the next cycle. If you remember, p implied q in Boolean logic, p implied q is equivalent to not p or q. So, we cannot make it fail non vacuously, sorry. So, this logic will fail if p is false, but p is false is not what we are trying to check here. We want p to be true and q should be failed. So, then you really have to satisfy this as well as this, all three of them you have to satisfy, the tool has to satisfy, and it could be a deeply embedded logic somewhere, and which is kind of the hardness of the problem. There are a lot of test generation method, I just want to summarize so that you kind of see what we are going to apply here. Of course, manual test writing is still prevalent in DSP community, microcontroller community, which is the robot community. They do not believe in any of these, they still do manually, because most of the instructions are so complicated, most of the control conditions are so complex, they manually write their test case. Random test generation is very easy, you can so quickly you can generate the test, but total time, if you look at the total time, test generation time plus simulation time, that could be huge. If you just consider test generation time, generating one test will take you 1 second, you hit the button, it gives you a test, any number. Formal method, which I am going to show kind of in a moment, it is good, but because it uses a formal method as the back end, it is going to have state space explosion. Then I am going to talk about kind of a semi formal method. There are many semi formal methods, I am going to talk about one of them, concolic testing, which is basically a combination of formal and semi formal. So, before I go further, the idea of formal and semi formal, I can give you an analogy. So, let us say you go home today and you see you do not have the key. Now, first thing you are going to do, you are going to say, oh, I was last in the classroom when I had the key. You are going to take your bike or car and very quickly come here. The taking the bike or car and coming very quickly is the simulation, and then you come to this room and you look very carefully all over the place, that is formal analysis, and after you do not find it, you said, oh no, not here, in the lunch time I think I had the key. Again from here you are going to very quickly go to the lunch place, that is again this going to the lunch place is again simulation, and then once you go to the lunch place where you had your lunch, you looking very carefully, that is basically formal. So, the idea of concolic testing is formal simulation, it is kind of in a loop of that in some manner, that is basically concolic. I will zoom into it, but is the key difference about these 4 major categories clear, and we are going to apply one of them, concolic, for activating assertions. So, let us first talk about how formal methods helps in this. So, let us think that your security condition that you are trying to satisfy, your assertion says decode equal to stored. So, your assertion was assert decode unit dot stall. That was your assertion condition. What we are trying to do, we are trying to create a test case. If we run that test case, this statement should fail. So, that means if you want to do formal method, you give the decode stall not equal, you write the negation of it. Give your design, give the negation of it, give it to a model checker. You know what model checker does? Either it says you are satisfied or it finds a counter example, and this counter example is nothing but a read after write hazard in an architectural sense, and that is the instruction sequence, and that is your test, and that test is guaranteed to activate this assertion. Only problem with this, so basically you get a test by model checking design and not property. Whatever vulnerability you are going to or assertion condition, you do a negation of it, you get the test. Only problem is because it is using model checker, whether you do use model checker based on binary decision diagram we talked in the morning, or bounded model checking based on satisfiability, all can lead to state space explosion when your design is complex or property is complex or their intersection itself is complex enough, which pretty much true for any large design. So, therefore, it is very difficult to use them. There are a lot of research, how do we control this state space complexity. I am going to briefly touch upon them just to kind of show you what people have done over the years, but then we move to concolic testing, which is what people are using today as we speak. So, what kind of stuff? So, this is basically an observation from Strichman. Strichman said that if you are solving or trying to find if there is a problem with somebody in your design in one cycle, and you figured out certain behavior, if you think this as a tree, you figured out that solution does not exist in the left subtree. If this is a tree, that observation will hold even if you unroll the design for 2 clock cycles. So, if you want to take analogy of a program, if for loop you are doing iterations, if the first iteration something did not happen, you are trying to see if anything happens second iteration, any observation, any understanding, any insight you got from the first iteration, that still hold in the second iteration. So, do not in the second iteration your tree would be much bigger, but it is the observation that the solution cannot exist in the left subtree, in SAT term that is called conflict clause, or so that situation still holds, and that is what it says. If the same property across bound or the size, or think about traffic light controller, car is waiting for 1 second, 2 second, 5 second, if something did not hold true for 1 second, it is not going to hold for 2 second, 5 seconds. So, then your search space, although exponentially it increases as you keep unrolling, but certain portions you can mark it black, you do not have to search. So, that is basically what Strichman has showed. Then there are many other works where different research group, including our group, we looked at. First of all, we are not trying to solve one assertion in a design. If design have millions of lines of code, it is going to have thousands or millions of assertions. We are trying to find tests for all of those assertions, not just one of them. And if those assertions have some commonality, so let us say you have an assert A and B, maybe another assert A and B and C, or A and B or C. You can have many properties, they might have overlap not by looking at the property, that would be misleading. The overlap is, if this is your design, if you consider the property, the kind of slice it cuts on the design, let us say A is one of the output. If you are trying to say something about A, then only thing relevant is from that output to all these inputs. These inputs are not relevant, this logic is not relevant, that is basically slicing. You could manually slice the design and run model checker. Most of the model checker today will slice it for you, you do not have to do anything. Now, so this is a slice for this property P1 or this assertion A1. Then for P2 it might be doing another slice, I am just randomly, let me take a different color. So, let us say it might be making a slice of this. So, then any learning or understanding you got from this part, no matter which property you solve first, that learning you can forward to the next property. So, this basically utilization of learning in the case of Strichman from one bound to the next bound, your first year of college to your next year of college, next phase of your life, from one property to another property. In fact, there are from one symmetry to another symmetry. When you have a multi-core architecture, for a classical example, if you are trying to solve that problem and based on that solution you figured out certain conditions should not hold, certain subtree is not relevant, you can solve the same thing for another core, or you do not have to solve for the other core, you can derive directly from the first core itself. If you do the job right, variable naming right, then you can solve for, if you have 32 core machine, you complexity reduce by 32, actually reduce more, because the complexity is actually 2 to the power 32. So, from 2 to the power 32 you reduce it to 2 to the power 1, and the solutions are still valid solutions. So, you can exploit symmetry across. Yes, please.
Previous slide. How do you transfer this property from one node to another?
Right. So, the way it works, so design and property or assertion that produces the conjunctive normal form, those clauses. So, design and P2 will produce corresponding conjunctive normal forms. So, the intersection of these two normal and then that is one thing. Second thing is we have some learning here, some learning L1, something we learned, that go to left, do not go right, do not talk to strangers, whatever we learned, that learning I can forward to the project property 2 only if that learning is relevant in the intersection of these CNFs.
But what are learning for A? You don't need the entire thing for B. Right?
We should not use entire thing from B. We might have learned lot of stuff. We should not apply all of it. That is why we need to figure out the intersection and figure out which learnings are relevant for B. Otherwise, it actually will misguide the next property.
How do you find out which is relevant?
So, that is the point. Relevant is this cone of influence or cone of intersection. Now, if the variable we are dealing with whatever, if it is a C and that C is completely contained in the intersection, because then that learning is relevant. So, the complexity of this is basically intersection time of CNFs.
But you are talking about properties, right, not variables. So
Oh, the property imposes the slicing on the design, property imposes slicing on the design. Eventually, you are solving for those variables only. So, that is the graph. If you think of a graph level, if this subgraph is also, because design is same, that is the reason. If design also was different, then all of these are useless. Design remains the same, property is different, but in fact properties are also not drastically different. If variables are different, output everything is different, then overlap would be 0. If overlap is 0, there is no learning can be forwarded. So, I am going to, so basically any form of similarity can be exploited. In fact, if you think about it, when you are solving for multiple property for multiple core, you can forward learning for from across the timescape, between the cores and between the properties. So, there is a lot of learning opportunity for reducing the time. But no matter what you do, problem with model checking or any of these approaches, any of the formal verification approaches, most of them they give the guarantee on a abstracted model, formal model. So, if you think about it, if you are a theorem prover person or doing PhD with a theorem proving expert, most likely you are looking at a design on the left hand side of your monitor, on the right hand side of your monitor you are writing in some formal language. It could be SMV, it could be anything. There are some automated tool SMV or COQ, COC or any of those you are writing that, and let us say you guarantee something. What you guaranteed on that formal model, not actual model, and the actual VHDL Verilog design would be synthesized. So, it is kind of a serious problem. We can argue, well, actually the formal model was automatically generated from the Verilog or VHDL to the formal, but it still it's a translation. Anytime you do a translation or abstraction, it would lead to potential false positive or false negative. So, that problem can be solved. So, that is what I meant by there is a need to translate a translation to somewhere, that is error prone, and also model checker cannot handle what we really want something like this, which is the concolic testing. What we really want is, if I have a design, it does not matter what this design is doing, if I want to activate a specific statement, our assertion, if I want to activate a specific statement, then the way concolic works is, first of all we instrument this one, instrumentation is a linear time complexity. So, for every statement, think about it, for every statement that is there, instrumentation will insert a display command, I am here, I am here, I am here, exactly the way we debug, I am here 1, I am here 2, you manually know here 1 meaning I entered the first for loop, here 2 means I entered the second for loop, you instrument that. And if you instrument the design, you do not change the functionality, because those are display commands or printf commands. Once you have that, then you run any random test, does not matter what test it is, you run, it is going to produce something, those instrumented thing, where you are, where you have been, which branches you covered, and so on and so forth. And then you kind of from that printout, you generate some constraints for a constraint solver format, and then you try to figure out, did I activate that particular display line, and if the answer is I did not, then you repeat this process. If answer is yep, whatever you printed, remember when you run, if I have, let us say, a simple sequential statement, easy to visualize, you have a if part, you have a else part, and when you simulate, let us say that that is all you have, if part and else part. When you simulate, you have only two choices, either simulation gone through this path or simulation gone through that path, that is it, no concurrency, no if statement inside if statement. So, the random test you run, let us say this is what you wanted to activate, something here, the simulation you did, if it has gone through this path, then clearly that printout will say nope, I did not get it. Then next time you simulate, you have to modify your test case now. You cannot run the same test case, because if you run the same test case, it is going to execute through the same path. If you have multiple if statement, it is going to go through same if path or else path, same chain or trace it will go through. Next time when I go through, I have only one choice in this example. Last time I need to flip this branch instead of going this. So, to flip this, I have to change to my test. This system will do that, this system of equation will flip. So, next time you simulate, it will go through the other path, and in this example you are guaranteed to activate that scenario. So, let me and but the thing I want you to understand is that concolic testing is designed to do branch coverage, that is all it can do, which are the branches can be covered. If I want to do assertion coverage, I have to convert these assertions and branches. It just so happen assertions are branches. If you think of assert request equal to acknowledge, it is basically if request to not equal to this, then $display assertion activated. You can always convert any assertion statement into branches, whether it is an immediate assertion which is embedded inside a sequential area, or concurrent assertion which is kind of inside always. So, then you convert that one as always, if something then something and so on and so forth, you can always create a conversion automatically like that. So, basically once you construct a branch, then I can run concolic testing and ask concolic testing to cover specific branches. And the way concolic testing work, let me see if I can do the animation. So, this is your design. By the way, concolic testing also works on software design. In fact, it coincidentally concolic testing started in software community. I borrowed it from software community and applied it to hardware community in early 2015, 2012. So, now it is used in both communities. So, but it came from Kaushik Sen from UC Berkeley, this idea of concolic, and the name came from the fact concrete and symbolic, the CON from concrete and the last part leak of symbolic. So, that is so concrete is the simulation, symbolic is the formal analysis, and you will see all of that now. So, basically you simulate first with the random value, and it just so happen, let us say random computation gone through this path. It took the if of all of the branches on the left, and all of these are if statements, and my target is right here. That is the statement, is the assertion statement I am trying to activate and find a test for. Anybody remember why do I want to activate the assertion? Why do I care? I generated the assertion, I put it in the design. If anything happens, assertion will fail and I will know. Why do I want to generate the test and going through all these pain? Go ahead, ma'am.
Because of the assertion also be false.
Assertion condition I might not have written correctly, so it will fail in a wrong time. So, I want to make sure the assertion I wrote, when it is supposed to fail, it fails correctly, it is a valid assertion. So, during design time itself I have to generate a test, check my assertion, so that run time there is no more false positive, false negative story. Thank you. So, now this is the path constraint, and then did it cover? I checked whether it covered, that is through symbolic analysis. If answer is no, I have three choices, this one or this one. There are many heuristics we developed over the years, different research group developed, and of course, this would have been nice, because manually visually you can see it, but in real life that does not happen. You might be thinking why not, if it is a control flow graph, if you compute a distance from the target, if I keep numbering, right, this is 0, this it happens to be same color, 1 second, this is 0, this is distance 1, this is distance 2, this is distance 3, this is 4, this is 5. If I compute distances 2, 3, 4, 5, 6, 7, 8, oh 8, sorry, I was doing wrong. If this is 0, this is 1, this should also be 2, distance of 2. But anyway, so if I know where I want to go, I need to flip the branch which has the shortest distance from that. So, ideally I should do that. This idea works if you can completely unroll the control flow graph, CDFG. Unfortunately, we cannot do that, because in a software design it is still easy, hardware design you have multiple parallel control flow graph there, and this target, it may look like this, but this target may not be activable in 2 cycles. It may be, let us think about it, if you write something in the memory, 20 cycles later if you read from memory, so there is a sequence of dependency. So, there is a 50 cycle, 60 cycle dependency, unless you unroll for 60 cycles, then do this kind of marking, then you know which branch is closer and which branch is far. The near and far otherwise is not obvious, but either way in this example the system will flip, sorry, let me do the animation again, system will flip that, and now when it flips, the original test case gets slightly modified just to make sure next time we simulate this branch would be included, everything else is not guaranteed. And let us say you simulate, that path got active, that path got simulated, and then our target is still not in that path, and again this time we are trying to do flip this particular branch, and then finally it will cover. So, really the key problem in concolic testing is which branch to flip. So, first problem was any security assertion we have to convert into branch coverage problem, and then second thing is once you convert to branch coverage problem, next aspect is how do you from that branch coverage problem, how do you get to which branches to flip to get to the target as quickly as possible. So, here is another animation just to show the first one, when you generate input, it basically took through a path, and then you want to flip, let us say this particular branch, then alternate path you have to solve symbolically what modification of your original test case will make you flip that path, and you keep doing that until you reach the target. So, basically I just summarize it here, when you have a design and the security assertion, you need design instrumentation which will print which path the simulation has took, then you kind of do simulation, and simulation trace constraint generation, you kind of do constraint solving, this is the formal part, simulation is the simulation part, this is the concrete and this is the symbolic, and then you basically get a test. Let us say your original test was A equal to 1, A is a primary input, then constraint solver said nope, it needs to be 0, of course this case it is a 2 choice, it is done, but normally it could be complicated lot of inputs, or A may not be a Boolean variable, it may be non Boolean, and eventually you get the test to activate that. It is just that it is doing it automatically. Now, normally most of the time people ask me this question, that let me just talk about it. So, scalability wise, so if you use any kind of existing model checker, one of the popular one is EBMC, then it is on, or versus you do the Concolic. Concolic is lot more linear, and this is kind of exponential when you. So, this is the AES design unrolled for different kind of depth. Let me skip all of that. Okay. So, before I go for dynamic refinement, let me ask try to answer one of the question most people ask, which is if this is my search space, my target is farthest away from the where I started. Maybe originally when you started, maybe this is how you are looking, then you are looking here, then you are looking there, then you are looking there. So, it is possible you have to cover the whole state space in the worst case to find the point. Then how is it Concolic better than formal method, which also tries to cover the whole state space? Would any of you attempt to answer that?
DFS method.
DFS method. Why DFS method is better than what formal?
Because it's go from starting with go from all the branches.
If you do not like DFS, we can do BFS, but the thing is, why is it DFS or a BFS, depth first search or breadth first search, better than doing formal analysis like what model checker does?
No idea.
So, the complex, it may look that way, but it is not true for two reasons. One is, formal method is trying to handle all of these millions or billions of states at the same time and then give up. If I put 100 or 200 kilograms on you, you may not be able to carry, but if I give you 10 kilogram at a time, sure you have to make 20 trips, you still be able to do it. This is the same analogy. It is handling one tiny part at a time, and theoretically extreme case it might have to go through the whole state space. It might take a long time, but it would still proceed. Formal will give up in the first few seconds, because it is trying to construct the whole design and unroll, and the memory in your computer, the size of the states machine would be larger than the memory in your device, and that is exactly basically state space explosion, but this will go slowly. That is one thing. Second thing is, in fact, in the worst case this will not happen. If your heuristics are right, then remember the branch flipping. Why would I be flipping this one, then this one, then this one? I should be flipping somewhere here and very quickly come closer to this and very quickly come closer to that, if we do it right. Of course, things are a little more complicated, that is one thing. Second thing is, the number of security assertions are in the order of thousands or millions, right. So, therefore, when on the way you are covering multiple targets. In fact, there are a lot of research in this domain. How do we cover multiple targets? Should we treat them as independent targets? Should we apply Concolic testing, or should we kind of rank order them and solve them knowing other ones you are solving? Think of the multiple property Strichman or other solutions in the normal model checking domain. Is this lot of such solutions exist. In software domain, people normally do uniform search. They basically start from left to right and as many of the targets as they can cover, and their case target is branches, as many branches as they can cover as they go sweep through. For our case, only difference is we are only interested in activating the security assertions, and we still want to cover as many of them as possible, as little time as possible. And even if we have to cover the whole state space in the story, we are doing one little chunk at a time. So, therefore, it is scalable. So, we stop for the break. Yes, please.
Sir, in the Concolic one, sir, it seems that the branch flipping, the better the branch flipping, the better this will be.
Faster you will converge, yes.
So, and that would depend on the heuristic that I apply.
That depends on the heuristics you apply.
So, sir, like some example of what are the kind of heuristics?
Okay, one example I already said. So, people use reinforcement learning that I discussed on the first day. So, machine learning is used everywhere. So, one of the heuristic is if this is target, you mark it as, let me do marking in a different color. If this is target, you mark it as 0 and this is 1, if this is 1, this is 2 distance, why this is 2, and if this is 2, this is 3, if this is 3, this is 4, this is 4. So, depending on where you are, let us say you are in this particular path, when you are trying to see which one to flip, you do not want to flip 4, you do not want to flip 3, you of course want to flip 2, the number that is smallest there. But the reason that does not work, because unless you unroll it, for software domain it works like a charm, but in hardware domain, because you not only have this, you have another parallel one, maybe another parallel one. So, it is basically the really the global control flow graph is a intersection of all of them. Think of this is a state machine, this is a state machine, this is a state machine, it is basically cross product of all the state machines you have to consider, and you have to unroll it for millions of cycle until the target becomes activated. So, constructing that, if you try constructing that, then you will have the same problem as formal method. So, that is why it has to be a lazy construction, do not construct something unless you have to. That is why these numbers is, I call it a heuristic, otherwise I will call it optimal, because if you are flipping this branch, what is the possibility that now we might say under what circumstances do you have to flip this? Remember, I might have to flip this, I might have to flip 3 to make certain conditions here, then something here will be activated, after that I have to flip this, then this branch will be activated, because think of memory read and write. Yes, this might be writing to memory. So, writing memory has to be activated, after that this reading component will get activated, and those are running in parallel, those are parallel finite state machines.
So, instead of
so instead of deciding about the distance from the node, if we think about the distance in terms of property, right. So, suppose I have say P1 and P2 and P3 condition, then it is happening, but your target is not P1, not P2 and not P3, right. So, I mean, is there any some kind of way I can distance, I can identify the distance between two properties?
Right. So, in this particular discussion, we are not talking about how do we make use of one property you already covered, how do we make use of, all we are saying we only have one target, this is where your assert statement is sitting, assert whatever that is. So, we are looking it as a branch coverage and statement coverage problem, that is how concurrent testing looks at everything, unless somebody fundamentally changes the paradigm. So, basically concurrent testing is how do we cover different branches quickly, so that I can activate that statement wherever it is, and in a scalable manner, going one path at a time. So, so this is one of the heuristics, there are many, there are at least I have seen at least 20-30 papers in software domain, hardware domain there could be might be 2 or 3 papers, many heuristics based on many other aspects of the design. We will visit in another 30 minutes. Thank you.
okay, so we'll come back again.
Good afternoon. In the last lecture, we talked about different ways of generating security assertion. Then we talked about that we need to generate tests to ensure that generated assertions are valid. Now, I am going to talk about once you have used this assertion for pre-silicon validation, should we just forget about them or there is some more utilization. I am going to talk about two utilization scenarios that many industries use, but most industries basically stops here. They basically for functionality as well as for security vulnerabilities, they primarily use it for pre-silicon validation.
So I have one question. So whatever assertions you have generated, what is the way you can guarantee that I have generated good enough assertions?
Very interesting question. So whether it assertions or whether it's properties, it's basically undecidable problem that it's covers the design completely. All it guarantees, if you have a coverage model, let us say line coverage, statement coverage, branch coverage, only from that perspective we can guarantee. But if we are trying to see, well, I generated 300 security assertion, does it cover all possible security vulnerabilities? Is it completely protected? Answer is no, there is no such guarantee, and same argument applies for functional assertions also. Even if you generate assertion or even if formal verification domain you have 3000 properties you checked, you can never say that my design is completely functionally correct, you cannot say. Only thing you can say, the properties I checked, my design is guaranteed to be correct for those properties.
So then what is the kind of procedure followed in the industry on writing enough properties thing? So formal method ensure that if the property is there and the design in no circumstances that violates that. So that way it is good, but if I do not have enough properties, then I do not verify the circuit properly, right?
Right. So let me talk about functional domain, then we will come to security domain. In functional domain, the idea is whoever is the verification manager, most likely the people who are professors like me, our PhD student, they sat and they write something called test plan. They develop the scenarios that need to be checked, and why does they come this scenario? They look at the architectural or whatever the design specification, and they kind of say, well, this design is supposed to do banking transaction, it should allow customers to withdraw money, it allow customer to check their balance, it allow customers to deposit money, whatever is spelled out, most likely each of that statement would be an entry bulleted list in that test plan. So then question becomes, for each of those scenarios, do we do a test generation and check it? Do we put an assertion for it? Do we formally verify it? But the starting point is test plan, and test plan does not guarantee anything. For rest of the company, the test plan developed by that verification manager is the golden thing. That does not mean anything, but it is better than having nothing. People are just randomly checking whatever they want to. Based on the original document, they develop a test plan, and then rest of the people in the verification team trying to make sure the part of the test, and test plan may include a sentence like, we need to have 100% statement coverage, we understand the branch coverage would be 98%, we understand the transition or state coverage would be 80%. So, they put a bar, they do not put, well, path coverage would be 100%, you can't do path coverage 100% any reasonable size hardware design. Software design it may be possible, because there are exponential number of paths, there is no way you can check all of them, right. So, test plan is the starting point, state plan is the golden thing. How do we know that test plan is complete? That is a different story. So, now I am going to talk about two scenario. Let us start with the so when you have this, let me go straight to the, let me go to the picture, then I come back to this one. Where is the picture? So, basically whatever we have gone through in the assertion, the question is, do we select a subset of the assertion and then we use it for dynamic refinement while the chip is in deployment, it is inside a device, somebody using the device. So, we are going to look at this two story, assertion selection and assertion refinement, but before we go there, the question is, ideally I would like to take all those millions of assertions and push it to the post silicon, so that in the device it is there. But the problem is, each of them is like a function. Think of it as a function you wrote and you want that function to be in assembly. All these assertions is nothing but a function call, and that function call would be sitting in the assembly. That is going to be lot of assembly code, lot of overhead in terms of code size, power dissipation and all that stuff. So, then that is why that overhead may be even hardware, it could be lot of area, power, performance penalty. So, then objective is, one option is don't keep any of them, get rid of them, and the way people get rid of them is by doing simply this. So, what they do is basically they do hash define, you add this sentence on top of your file when you are done with your, and it is basically the comment line or whatever it is. So, then that assertion call, all of the assertion call is basically become a comment, and when you compile, compiler will get rid of it, it is gone, you do not have to manually go and delete them, right. But as I said, this would be a easier solution, but you may want to keep some of them to keep the guarantees, even if you formally verified. So, the one other thing industry does is that this is my test plan, or this is the, let us call it test plan or whatever verification plan. In that plan, if I want to do a Venn diagram, out of this plan through my formal simulation whatever it is, I am able to check this part, right. Sorry, I am able to check, I am done with this part, this is done, but this part is still not done. For whatever reason you could not verify it, you could not check it, those assertions companies want to keep. At least safety critical system, that is how it is done. If you want to check 10 properties, 8 of them you can formally verify, good. The 2 you could not verify, you want to keep them in the design. Otherwise, the safety critical requirements is not met. If any time anywhere the problem happens, you at least know immediately. Now, then the next question is, if I want to keep some of them, which of them and what can we do. So, here is some study I wanted to show you. So, basically obvious story would be, if you map 100% of the assertion, you keep 100% of the assertion, you get 100% of the coverage, whatever those assertions, if you call it assertion coverage, whatever it is trying to cover, functionality or security vulnerability. But it turned out through different kind of scheme, the SS stands for signal selection, because I did not talk about, I talked about trace buffer, but in that trace buffer how the signals are selected, which one will be traced. If you do that smartly, then it is quite possible that even with mapping 60% of them, you can get a 100% coverage. 100% mapping 100% would give 100%, that is understood. Even 60% of assertions if you can keep, that would give you 100% coverage. And so, that would be if you do smartly. In fact, it can be even better, if you kind of focus on hard to detect events. So, if you are focusing some rare condition, hard to detect event and all that stuff, if you choose your coverage monitor from those areas, then it is going to be even more interesting. So, for example, if you have an assertion which is checking A, another assertion which is checking A and B, it is kind of little difficult to kind of figure out which one to keep, which one not to keep, unless you know that A is a very A is a very B is a rare variable. If you know B is a rare variable and A is kind of abundant, then you want to keep this one. Then it is a rare event, this is not so rare. So, therefore, even when this one is getting activated, there is a high chance this also will get activated. So, if you kind of do which property kind of consumes the behavior functionality. So, functionally none of them covers any of them, but from a coverage point of view, think of inside a if statement which where if this is a straight line of code and if there is a if statement which has two branches, if you keep this one, all these persons are supposed to be covered anyway. So, you do not need to keep those assertions if you keep either this, but if you select this you can't talk anything about this. So, there are those pros and cons. So, based on certain methods if you do it right, then from 60% you can also reduce to 30%. Now, 30% is still large, but this is the kind of step some companies use. In fact, companies like IBM use this methodology not to keep in the final silicon, but something for acceleration. So, those of you kind of worked in the field of verification, you know there is this simulation and then there is certain little more speed up is on acceleration, and then there is lot more speed up 100x speed up on emulation. So, there are like Cadence, Palladium and all those $1,000,000 machines if you buy, if you have a really large design, it takes time to map to it, but once you map to it, it really runs fast, very fast. You did not fabricate, you did not have the chip, you still have your VHDL, Verilog design, operating system, all of that, but you can run very fast. If you do simulate with real world applications, then it is going to take weeks or months to run one scenario, one test plan, one scenario. So, if you map it to the emulator, then what these companies do, they try to minimize the number of assertions they put on the emulator, because remember emulators run fast if you do not talk to them. If you talk to them, meaning emulators have to read something from keyboard or display something in the monitor, then it's think of it's like a breakpoint. It was running very fast, suddenly somebody running very fast, you said can you slow down, take a cup of tea, just have one sip, you slowed that system down to produce certain event, consume certain event, then again starts running. That is why minimum number of IO would be ideal for stimulation. So, it is not really the fabric. So, after emulation when everything is fine, then they synthesize and then finally you have the chip. So, they do not keep on the final version, but they try to select a small set in the emulator version. So, depending on which company, what is their usage scenario, what market they are trying for, they try to keep certain variations of assertion. By a vast majority of companies get rid of all of them after pre-silicon. Any questions? Whoever wants to keep, they try to employ different strategies to reduce. How do I reduce? Which one are most important for me? What am I can live without, what I cannot live without. So, that is one way of minimizing assertion for using in an emulation environment or post silicon. The second one is even if you map somebody in post silicon, because there is a dynamic circumstances, the way you use your phone, the way I use my phone is different, but when company produces it, they produce and optimize it for the average scenario. They have some average analysis. So, typically people make 20 calls a day, 100 text messages and all that stuff, but as you realize each of us usage scenario is totally different. I probably make 2 to 3 calls a day, text 4 to 5, and it is just me versus you. Even me versus me, maybe morning I do not use my phone at all, only in the evening. Maybe I do not use the phone at all during the week, only during weekends I call all my family members. So, the usage pattern of any device can change from people to people, from day to day, even within the day itself. So, then question is what was customized or optimized for average scenario that is probably not a beneficial way of utilizing power and all that stuff. So, that is the similar analogy applies for assertions. The assertions you mapped, all of those cannot be fired. Think about it, you have an FPGA fabric and you have a choice, and let us say you decided a small subset of 100 of them, but FPGA cannot map the bit stream. If you recall the way bit stream was mapped on FPGA, we cannot map all 100 of them at the same time, we can map let us say 5 of them. Then during run time, which 5 do I run? If I am making a call, maybe certain vulnerabilities are relevant. If I am texting, certain other vulnerabilities are relevant. If I am playing video game in my phone, certain other vulnerabilities are relevant, and it can change days, months and usage scenarios. So, then is it possible if I start with 100 vulnerabilities, remember the bit stream for these vulnerabilities are already there in the memory. The FPGA need to take it and put it in corresponding lookup table and map it, but because of the resource constraint it can let us say from 100 it can do 5, 10 whatever. How do I choose 5 from 100 while system is running? That is the problem of dynamic refinement. I want to distinguish what I talked earlier, that is a static selection. Statically you are deciding who supersedes whom and all that and done, that is a easy problem. This one is a much harder problem. Let me see if I can motivate that while you map it is a harder problem. So, now I am going to talk about dynamic refinement. This I talked little bit, but I made see little bit of it, but this synthesis map all that you just put it on the device, fabricated, and dynamic refinement is working while this chip is working in the system itself. And dynamic refinement is a common idea in any embedded device or many embedded devices in some form. So, the question is selection of profitable assertion and refinement. So, selection of profitable assertion, here is another way. I talked about the different way through signal selection and all that, but another way is there a way to cluster. Remember in unsupervised learning we had the notion of clustering. So, can we cluster a set of assertion and say they are kind of covering similar vulnerabilities? Once you cluster them, then can we talk about a dominator? If I in this cluster, if I trace or select or activate this assertion, then other assertions are kind of covered. It will not be covered exactly, but kind of covered. So, that is basically the story of clustering using unsupervised learning and selecting the dominator during runtime. But if you want to do dynamic refinement, the key problem is we have to solve this problem. What we are trying to solve? We are minimizing from that whole set S, we are trying to find a subset such that the power of that subset or whatever power it consumes below the power budget and the area below the area, there may be more constraint. And if I have to take some number, let us say in the system I have assertion A with kind of power profile, let us say 3 milliwatt area, forget about milliwatt and millimeter square, let us just put some number. There is assertion 2, let us just say this is 2, let us say the assertion 3, which is let us say 4, and let us just say this is 3, right. If my power budget is 5, then I can take, if I take A3 I can't take anything anymore, I am done, because it is already 4, none of the addition will make it 5. If I take A1, A2, then I am pretty much done, I can't take any more, but I still have to make sure if my area budget is 3, then I can't take these 2 either, right, depending on what is my area budget, what is my power budget. And then there is one more problem, let me see if I go forward I will come back, which is the problem would have been easier if this were, I will come back to this. So, problem would be easier if things were cumulative. So, what you are seeing in this diagram, the blue things are the kind of cumulative. So, for example, if I use 8 of the assertion, the power consumption should have been something like 0.07, but in reality it is 0.02. The reason being when you do cumulative, you kind of think that when the design gets synthesized, it is like they are independently sitting in separate places. But you know how compilation work. If one of them is A and B, another is just A, probably the output of the A would be taken for the other assertion. It is not going to build another copy of A somewhere, A and B another. So, because of that optimization, actual power is not the cumulative one. If cumulative, it would have been wonderful. Because it is not that, because cumulative story does not work for neither for area nor for power, actual numbers are drastically different and you do not know that number until you implement it, synthesize it, map it, measure it, you actually do not know. If you do not know, then all these 100 situations you have, if you are going to choose 100, choose 5, that is an exponential number. 100, from 100 you are choosing 5 of them, 10 of them, whatever dynamically. You need to maintain a table of that exponential number table, all possible combinations of 5 and their area and power number. So, that dynamically some software can figure out which one do I choose and add, because otherwise it is not going to work. You cannot simply do cumulative addition of 5 of them to figure out if it is matching or not, because of that non-linear relationship. Let me go back to where I begin. So, it is basically a minimization problem. Basically, it is a minimization problem where you are basically trying to select a small subset from the all possible assertions that are already there in the FPGA memory, from FPGA memory. So, if this is you think of FPGA, remember we talked about it, we have this reconfigurable blocks, reconfigurable communication, and what I did not show you, there is FPGA memory, and from this FPGA memory, this bit stream or selected bit stream, a set of them will be pulled and mapped dynamically, 5 of them out of let us say list of this 100, 200, it is just a number, whatever number it is. That mapping process need to satisfy at least these 2 constraints. For example, it could be more constraint. It is a multi-objective optimization problem. So, this is the subset of the checkers, this is the cost function, this is the power function, and this is the area function, and this is the power constraint, this is the area constraint. Now, how do we, so cost calculation and so how to compute the function a, p and a, given that there are 2 to the power n possible inputs, because you have to try all possible kind of scenarios, and then optimization problem is once we have this story, how to find the set that minimizes the cost while satisfies the constraints. And this we can use regression. If you recall the regression problem, the analogy I took, you are trying to predict the wind speed, not just whether it is a cat or dog, not the Boolean answer, not a classification. It is basically the regression problem. You are going to select a number, and for optimization problem it is a gradient descent. Remember that hill climbing, you are basically taking step function and going down. So, it is all machine learning concepts, and this is the of course, this involves model training, but the key idea here is that can I train a machine learning model which will tell me if I choose these 3 assertion how much area would be, instead of building an exponentially large table, doing exponential experiments offline before your device starts, and keeping a huge table in FPGA with different combinations, and FPGA will choose one of those combinations during runtime, which is kind of infeasible. We want to train the model, assuming model is tiny enough, and then we ask the model during runtime, if I choose this 5, tell me what would be my area and power. Now, of course, this has overhead of keeping the machine learning model itself, and the way people look at it, people kind of think, well, this there are many other applications people are keeping machine learning model anyway, it is all there, machine learning accelerator will make use of it or make use a similar version of it, right. So, cost prediction, as I said, you do take a subset, synthesis, simulate and train the regression model. This is the training part. And then, so here is a story I am trying to show you. For if you are going to choose 4 of them, yes please.
Why this assertion takes area?
Assertion is a function. So, whether you implement in software, it is going to be some assembly code. If you implement in hardware, it is going to take some area.
That's a condition check, right?
I mean, in programming language, assertion is implemented as a function call. When you say assert, file pointer, anything you say, this is a function call. I mean, conceptually this is if that function call, inside that if floating pointer equal to null, then you basically just print something, then you exit 0. But this is still a piece of code that will consume the implementation overhead, whether you see as a bit stream, whether see it as a assembly, that would consume area.
But this must be negligible in context of overall area.
If you map one assertion, yes. If you keep one assertion, and again remember the things are, assert FP is a simple example. Most of the time the assert condition is actually complex, and those variable would come from different places. If you map it in FPGA, that will come from different lookup table, lot of communication configuration, it would have a lot of overhead depending how they are placed. So, if you think of 4 kind of assertions, then there are, if you have 4 assertions and you are trying to take, there are different kind of scenarios. So, for example, if the scenario is we are going to take 3 of them, and or maybe another 3, different 3, or it could be another 2 of them who will satisfy my requirement. So, there are many possible such scenario. For each of these scenario, I need to compute the power and I need to compute the area. And if you want to, and all of that has to happen during run time. As I said, you can maintain a huge table, or you ask the machine learning tool to predict these power and area numbers. Then your question becomes, if I have a trained machine learning tool, what is the overhead of that machine learning sitting in the FPGA and how accurate it is. That is all that boils down to. And so, then basically then when you solve the optimization problem using the assuming the machine learning can give me the numbers for the sequence, then I kind of choose which 5 do I choose, this 5, that 5, this 4, which one do I choose. For that if you recall gradient descent, you are simply basically from a mountain top, you are simply kind of, if you imagine you are just going down, that is the ideal situation. Every step you take, you get closer to the valley, if that is your objective function, but in reality that may not be the case because of many other deviations, and every turn you might have multiple choices. So, most of the people what they use is gradient descent with simulated annealing, and the idea.
What is the actual, so earlier part I understand that you try to select a subset of the assertions which you want to check later, right, maybe
Yes.
for emulations and all. But here you are also again try to select a subset of the assertions, but in which phase of your design
Right.
process?
So, the emulation and all that stuff that could be done for even for post silicon, that you keep them and all of them. If I can keep executing all 100 of them, there is no problem. If I cannot afford, then 100 I know important and needed for post silicon, but I can't afford to run all 100 of them at the same time. That is the dynamic refinement problem. So, therefore, you have the bit stream or how to implement that information you have, but they are not active at this time, and the active area, let us say you can map only 5 of them. Then problem boils down to, based on my usage scenario of my device, which 5 do I choose at that time and map so that they monitor. If I am drinking a coffee in a public Wi-Fi area, then the vulnerability that is happening. If I am using my phone in my own home Wi-Fi, the attack surface is different. So, therefore, the situation is different, and if system is smart enough to take advantage of situation awareness, which 5 assertion it want to keep activated.
So, this 5 you are talking about will run on emulation or in post silicon?
It is post silicon, and this could be even for emulation, but we are saying is first let me just say first we have 1 million. So, 1 million let us say we reduce to 100. So, this is one story. Emulation post silicon, if I can afford all 100 I will map. If I could have afford all 1 million I could have mapped all million. Whatever subset I do I can do that. Now, the scenario I am talking about the subset I am trying to map, even I can't execute that. Then my question will be okay, take 1 million and map 5. The problem with 5 is I could have done that, just take 5 and put it, because the usage scenario changes, that 5 could be meaningless for many users. Meaningless where when they are accessing their phone in the airport or accessing the thing in their home. So, there is no dynamic reconfigurability. If you want to have that feature, then you basically you map more or keep more, but actually you activate only a subset of it. So, this is also subset selection, this is a dynamic or runtime, this is a dynamic one, this is a static one. Because it is dynamic, then I need to kind of figure out how do I select them.
So, it is basically those 100 is already there inside
already
the bit
there
stream.
in the FPGA memory.
In the bit stream.
In the bit stream format.
Okay. That means you have already implemented them, right?
You already implemented them in the memory.
Only just to reduce power consumption or maybe the timing, you try to select subset.
They are not mapped to the lookup table.
Okay.
So, where am I? Yeah, so gradient descent with simulated annealing. So, basically instead of the step function, it is basically kind of random feasible steps, and the way you want to visualize, the way you want to visualize, typically if you think of any minimization function, this is classical from any optimization book. In any optimization book, if you want to do any minimization function, what is happening? So, depending on where you first started, you do not know where you started. So, if you started let us say here, then no matter what hill climbing you do, you are going to eventually go to this one. If you do normal gradient descent, you are going to get stuck here, because anything else you try, it is going to be a bad solution. So, when you do simulated annealing, you kind of do bunch of random jumps, you take some risk. But then you try, remember here we are not trying to get the maximum, we are trying to minimize the cost or any of those. So, then you are kind of you might have to do one more random jump, because here you can manually physically see it. When a solver is solving this, they do not see any of these values and things. So, somehow somewhere here there has to be a random jump, and then it needs to reach there as quickly as possible. Most of the time the solutions get stuck here, that is why people kind of combine. There is no guarantee, but simulated annealing will have that effect, that random jump is supposed to have, and research shows and people usages. Now, so here are some results I just want to quickly show you. This I already talked about. So, cost prediction, how well does it predict the cost, and if you can see most of the kind of there are some of the regression and linear regression with quadratic interactions, there are few machine learning models. As you can see, most of them the prediction error, this is, think of this as an error, this has a big name, normalized root mean square, but think of this as a error. So, this error is really very small. Here is little high, but you can still think of it is kind of less than 5% error. So, for so this is power consumption, this is area. Machine learning predicts when you select any set of thing how much area or power it will take, that prediction accuracy is basically somewhere around 1% for power and kind of 5% for area. It is not great, but it is better than you just doing simple addition or maintaining exponential large table. So, there are for dynamic refinements, basically if So, for different benchmark of course story is different. If you really want to minimize your power or so this particular case it is trying to do coverage, your coverage basically goes high if you can relax your power consumption. If you focus on any of the diagram, the power consumption if you allow 0.135 milliwatt, you might be able to reach 100% coverage using even that small number of thing. But if you tighten your requirement, well my system will not allow more than 0.115 milliwatt for the assertions itself, then the coverage boils down to like I do not know I have to read this 3D, maybe like 40%, 30%, it drastically goes down, and that should not be surprising to you. More restrictive set the choices, so it would be able to map less number of assertion, it will have kind of less choice. But every design, if you can see this kind of portfolio where the so maximum LUT is the area, this axis is area, this axis is power, and this axis is how much coverage it can give you, your vulnerability coverage. So, that is why the dynamic refinement problem is an interesting problem, and it is academically definitely interesting, and it is hard to tell whether different companies are using it or employing it. Any questions?
So this is for only for FPGA.
So, ideally the question is it only for FPGA? I took the examples of FPGA, but dynamic refinement as long as you have a reconfigurable fabric, and because today de facto reconfigurable fabric is FPGA, if there is any other reconfigurable fabric it should work.
So, something cannot be done in software?
You can do it in software, but if the software speed is acceptable for the device in operation.
Only assertions, only for assertions. Anyway, assertion is a software functions.
Right, but
some but just can be put into software.
Right.
Because
so
dynamically you are doing, and ASIC fabric may not allow to do, but can you do something in software?
So, the software that basically means you have a set of functionality that running in software, and that software you have a set of assertion, you can selectively turn them on or selectively make the comment statement, you could do that. Which one you turn them, so if you have a software program, so this idea is all same. If you have a set of program and you have assertion here, you have let us say 4 assertion, you want to activate only 2 of them. So, that boils down to this removing this comment line for 2 of them and keeping the comment line for the remaining
but
2.
For hardware maybe, but
No, even for software.
after you
in
design
the assembly, it is a commented assembly for 2 of them, which one you comment, which one you uncomment, that is basically you can decide based on the same gradient descent and those minimization algorithm dynamically if you want to decide.
No, my question is, once you fabricate the things, so you do not want actually any other reconfigurable fabric, but do it in software kind of thing. So, if you are designing for ASIC, what I can say RISC-V processor or some kind of processing environment.
Right. If you have a processor, then only possibility is the processor is running those assertions in parallel to whatever other hardware is running, whether it can do at speed interaction with the hardware devices, which is highly unlikely. So, just kind of to conclude this one, for assertion based validation, what I covered so far is basically it has 3 important components. Once I know the vulnerabilities, how do I automatically generate security assertions? Then how do I make sure those assertions are valid? And finally, can we use those assertions or a subset of those assertions in my post silicon environment like devices in deployment? And most of the work today, if you look, most of them are using large language models to generate assertions for different capturing different types of vulnerabilities, either using large language models for detecting vulnerabilities or large language model for generating assertion and embedding them in the design automatically. In the next lecture, so today's lecture I am going to talk about firmware security verification, and I am going to make use of these assertions for designing, but the primary focus of this one would be firmware. What is firmware, where is it, we have some brief idea. Now, the question is how do we verify using some form of properties or assertions. So, we briefly talked about that any device you look at, if you zoom in, then basically it has a set of actuators, sensors and firmware basically between hardware and operating system. It is basically go between. It initializes the states and then it basically enables communication between hardware components and application software through operating system. That is basically its job. Now, when we try to verify firmware, it is kind of tricky, although if you look at it, hardware we kind of know, either it is fabricated chip or VHDL Verilog. Interestingly, firmware is nothing but C program or your favorite program in your favorite language. So, the first thing that will come to your mind, well, if it is software, then this is software verification. Answer is no, and I will try to give that flavor to you. It is actually not. Firmware is not a software, because software you can apply input and you can test it, firmware you cannot. You cannot apply input, because the kind of environment it operates, like the BIOS kind of thing, if you think of the kind of environment it operates, because of security requirements, the kind of constraints imposed on it, you actually cannot apply anything on it. Think of it provides some hooks that connects to hardware and talks. So, when you say, well, in that hook I will put some value, that is not going to work. It has to be, you have to put it with the hardware, otherwise it is not going to work. So, the closest you can do, your C is running and VHDL Verilog is running together, that is the closest you can do, because just applying some values to the software is not going to work, and also depending on the thing we will talk about it. But the key problem even in firmware verification boils down to same that we talked in formal verification, and you will see why in a moment. But let me explain to you this state space explosion problem, which is a problem for hardware verification, problem for formal verification, it is also a problem for firmware. So, in one clock cycle, if you know what needs to happen to firmware, it is working with hardware. If you unroll in 2 clock cycles, something happen. If you unroll for n clock cycle, it is a lot of space that need to consider. For a normal software, it is sequential logic. You can argue it has some state machine, but mostly sequential, things are simple. Once you make billion lines of code, it is sure it is complicated, but in firmware it has to deal with the complexity of the hardware. That is why let us talk about how do people do it today. So, this is basically how people do. There are 2 popular approaches, all the hundreds of papers that has been published, I can put it in 2 buckets. First bucket is manual abstraction. So, how the manual abstraction works? If you know what scenario for the firmware you want to check, then you take a version of that hardware run with the full firmware. So, this is the full code, full firmware, all of it, but this is not the full hardware. So, how would I say? Let us say your hardware is a processor, but this firmware or the interaction you are trying to check on the firmware deals with only adder. So, think of this is just a, either think of add operation or just that adder implementation, that is it. Manually you abstracted, nobody did automatically, you manually abstracted, give the full firmware, give that adder functionality, and then that verification can be done. This could be multiplication, but this manual effort of kind of separating it, and there are a lot of work from Sharad Malik on instruction set abstraction level based thing. So, once you have a set of instruction set, you basically keep only the instructions or the part of the instruction set that is relevant for this particular scenario, whatever scenario you are trying to check. Remember, this scenario is same as assertion, it is same as behavior, same as property, but manual abstraction is the hardest part. If you do it wrong, everything is wrong, and as you realize, because it is in the abstraction level of instruction set, it does not understand pipelines, caches, branch prediction, it does not understand anything, but the actual firmware has to run on the real thing. So, you are not testing on real thing, you are testing on an abstract model, even if it says it passes, there is no guarantee. On the other hand, people are saying, well, I mean, if this assertion scenario or this scenario is addition, all I have to tell the tool whichever solver, formal solver solving, I just have to say, well, do not focus on the whole design, just focus on the adder, and the tool would be able to figure out, okay, this portion is adder. So, let me get rid of that automatically. So, it has to manually provide a hint. For every scenario you want to cover, you provide a hint, then the tool, internal formal verification tool, do the partitioning and get rid of everything else. So, this is equivalent story as this. Instead of manually giving this, during solving process, tool itself gets rid of the irrelevant stuff. So, that is you still have to provide that hint. Yes.
Sir, in this, sir, the formal verification we have carried out.
Go ahead.
Sir, in this, sir, like the formal verification that we learned previously, sir, that was being carried out pre-silicon. Now, sir, we are trying to abstract the hardware and then carrying out formal verification. So, formal verification we are carrying out on hardware post-silicon.
No, this is pre-silicon. Formal verification cannot be done post-silicon.
So, sir, how, like you said, that abstracting a hardware and then.
Right, I keep saying hardware, this is, think of a hardware model. In this particular case, this is not even VHDL Verilog code, this is simply instruction set. It is like add, R1, R2, R3, or the functionality for that add functionality, that is all it is. That is why I drawn that diagram and said this part of the code, VHDL Verilog code. You manually abstract or you give a hint which will do the abstraction for you, right. So, if you give hint, then you can take the full firmware and you can take the full hardware, that is a good news, right. So, yes please.
I have a question.
Yeah.
Sir, like whatever firmware we will take, that firmware is only for either or it will be for the whole system basically.
So, I am trying to focus the problems, but firmware is for the whole system. So, in the car example, firmware is supposed to initialize different actuators, different sensors, read data from sensors, of course, with help of other people, but this is the sole responsibility. Whatever operating system does, if you look from application perspective, but if you look from hardware perspective, that is basically firmware.
Yes.
Firmware is the operating system if you are looking from the hardware side. If you are looking from the program side, that is really operating system, which is basically scheduling which program will run, who will stop, how will context switch, what will happen. Applications do not see firmware, but firmware's job is to initialize different control register, setting separate bits, communicating data, transferring things, taking care of everything. It is the operating system from, and it also does a lot of other things. Whenever you design the system first time, the BIOS, that is the area where it sits. Whenever you buy and you want to install the Windows, whether you do, sysadmin does it on your behalf, that BIOS checks all these stuff. Is it a legitimate operating system? Should I execute it? Is it compatible and backward compatible with the previous one? Can I do rollback? It controls all of that. And the worst part is, it has to take care of itself also. If somebody is saying BIOS need to be upgraded, before upgrading itself, it need to check its health, the health of the person coming in, because if somebody coming in and replacing me, I need to make sure whoever is coming in and this superpower actually trustworthy. So, this firmware upgrade, anti rollback, it has a lot of functionalities which is not natural for any software program. You think of bubble sort, insertion sort, average computation, Fibonacci series, that is not they do. Check your health, check others' health, allow upgrade, decline upgrade, all of that it needs to do. It is an extremely secure environment. It is more secure, more privileged than operating system. So, now there are a lot of stuff that can be done. I will just touch upon some key ideas to kind of show how can we do hardware firmware thing without doing abstraction. Like the way concolic testing did, we actually tried to do it is not concolic testing, it is a verification hardware firmware security co-verification framework that we can do. Or if you think of the previous example, can I automatically generate hints? So, this whole scalability issue, when you have a lot of hardware, how do I take care? What is the key idea is, based on the formal verification ideas I gave in the morning, you will be able to understand at least in some layman terms. So, when you have an implementation and you have a specification, you manually you construct some formal version of them and you try to check are they equivalent. But the thing is, because you are operating on the abstracted model, even if it says equivalent, you do not know if that is true. But the only good news is, if they say there is a failure, that is valid, otherwise nobody will use such approach. If they say it is successful, that does not guarantee it is completely successful, but if it finds a counter example, that counter example is valid on the original design. That is the good news. What we are basically saying, if you want to do on the actual design, can I break down the from full system to module level? Even within each module, think of a processor as fetch, decode, execute. Can I just solve the problem on the decode? Even within decode, can we just solve based on scenario? What are these scenarios? Remember this assertion? Assertion is checking one of the scenario. So, can we check for one of the scenarios? So, then if you think of slicing, first you reduce complexity at the component level, then you reduce scenario at the abstraction level. Now, then you put the symbolic execution. So, for example, if in a calculator, if you want to kind of verify all possible scenario, it is really a lot. But if I tell you, well, can you check the only add operation for me please, then you are basically trying to figure out which path to check, then it kind of becomes tractable. Now, this scenario based, so at least this tool is also Hive is also open source, you can play with it. So, the scenario, the good news is this system does not know anything. You give it a scenario, you say 2 plus 3 equal to 5, you give just this scenario. One operation you tell the system will figure it out that I need to verify add. What is the difference between this and so this seems like a test case, and it may seem like, well, then what is the advantage, how is it a formal verification? If you give a scenario of add, this system will check 2 to the power 128 possible scenarios for the adder. It did not cover all possible scenarios, it did not give you a guarantee, but it gave you a guarantee all possible additions it will check for you through symbolic execution. But you have to provide scenario. If you do not give scenario, so then problem, still the research problem you want to pursue, how do I create different scenarios? So, if you give add, it checks all the possible additions. If you give multiply, you still have to know what operations that system support, what are the scenarios you want to check. Then this scenario level decomposition and verification, that basically becomes an important story for firmware and hardware. And recall, firmware has to run with hardware. Independent verification of firmware has no meaning, it does not even make sense. Now, another way to visualize where we are getting advantage, let us say from input of the story to output, there are a lot of modules are involved, lot of state machine transitions are involved. If I tell you a scenario, maybe only 1 or 2 of the paths are relevant, you are basically telling your solver, constraint solver, please focus on that path. That is what our teachers, our parents tell us, please do not look at left, look at right, all that attraction, materialistic world attraction, stay away from them. You are basically focusing, if you are focusing on solving addition, you just focus on addition, you do not focus on other scenarios while you are solving the problem. So, if you can think about it, during solving time it is actually doing the slicing, auto slicing. So, I just wanted to show quickly too before I for solving this problem full blown, there is an assumption I did not tell you, which is this is applied to IoT devices. So, IoT devices such as this backup. So, it is a full system, because remember firmware verification is meaningless unless it is in the full system mode. So, this is a RISC-V CPU, some RAM, some ROM, an external flash hard disk, and this driver, flash, cipher and all that, and all of it can be fully formally verified with the firmware. So, same thing, but if you do not do this kind of approach even for such a simple system, first of all RISC-V, if you look at it, it is really large amount of code. Then this one is elliptic curve cryptography. The day I discuss the cryptography, you will get better idea. This is RISC-V, elliptic curve cryptography accelerator, and then ROM, which has the firmware and different type of elliptic curve cryptography arithmetic, SA. This is basically their authentication, ECDSA and ECIES. So that is another module. This one is liquid crystal display controller, again similar thing, only difference is the different types of drivers or the drivers that firmware interacts with. Remember, whatever external device you put in, they will have driver. For that device, from that device perspective, that driver is the operating system. From hardware perspective, this firmware is the operating system, and by the way, these devices there is no actual operating system. There is no actual operating system, because the applications that they are running, that is pretty much it. Same thing we have done for the serial advanced technology SATA controller, and again it is all the different media, different storage, and how do you connect the cable, and that is kind of the scenario. And that is pretty much all I have for today. If you have any questions, I will be happy to answer.
So, is these firmware codes are available publicly?
Firmware codes are publicly available, at least for majority of the devices. Public the RISC-V based devices, firmware codes are available.
Those are basically the BIOS, whatever they are research in BIOS.
Those are the BIOS and written in some variation of C or some variations of C programming language. The things that I did not talk about, so verification of this firmware, because you can't apply for primary input from hardware through other interactions, you have to activate certain functionality or assertion, and if you try activating from the input, then it would be state space explosion. Instead, what we do, whatever you want to activate, you start from there. So, if I draw pictorially, if this is your firmware, if you think this is an entry point, and if you try to reach there are different function call, different assertion, if you try to go from here, there would be state space explosion. Instead, if you start from here and keep going, remember you do not have to come to entry point, because the way firmware works with hardware, this could be the boundary itself, interaction boundary with hardware. So, you start from actually what you want to activate, and then keep going until you find some interaction point with the hardware, and then that is how you verify. Then you figure out what needs to happen in hardware for this precondition to happen. You start from the actual target point, then from the entry point of the firmware, and try to reach a state space explosion, and that is one of the reason nobody works in firmware verification. Any other questions? Thank you.
Okay, so we are done for the day. Second, another long day. Lot of verification knowledge.
That's all. No more verification.
And verification is hard, right? So I think at least you get an idea that what are the various way you can verify and how hard it is, right? And if you try to choose your career in verification, there are a lot of exciting opportunity, but path is little bit difficult, right? Risk there. Anyway, so you enjoy your holiday.
Language model, path is very easy.
Yeah. So yeah, enjoy this Friday and Saturday break. Sunday they can come back here at 10.
Just ask how many of them are coming.
I think as per his 30 is coming.
All of them.
Almost everybody is coming. Okay, thank you.
The tremor is from another part is drivers. Most of the drivers are free. Most of the times the company provides. Manufacturer design hardware, they generally give drivers. Tremor and driver. Driver C code are most clear.
That will Monday will check. I think how many are want to do exam? I think 3 or 4, right?
True.
Sir, you have to set question.
Yeah, setting questions for 1 or 10.
Right? Something will happen. So last Friday, last half we'll do something.
No, but I will have to grade.
We'll grade. Something will happen.
Okay.
But around 10 we'll give the exam, right?